The Great Attractor. Let me tell you about something that's pulling you right now. Not metaphorically, literally pulling you through space at 2.2 million kilometers per hour. It's called the Great Attractor, and it's one of the most frustrating mysteries in astronomy, because we can't see what it is. Here's what we know. Our galaxy, the Milky Way, is moving. That's normal. Everything in space moves. But we're not just drifting randomly. We're being pulled in a specific direction, toward a region of space about 250 million light-years away, in the direction of the constellation Norma. And we're not alone. Thousands of galaxies in our cosmic neighborhood are all being pulled in the same direction. The entire local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, is moving toward this thing. So is the Virgo supercluster, a massive collection of galaxy clusters. We're all flowing toward the Great Attractor, like water circling a drain. The speed is what gets me. 2.2 million kilometers per hour. That's about 600 kilometers per second. At that speed, you could travel from Earth to the Moon in about 10 minutes. Something with enormous gravitational pull is causing this. When astronomers calculated how much mass would be needed to pull all these galaxies, they came up with a staggering number. The Great Attractor would need to have the mass of tens of thousands of galaxies. So why can't we see it? The problem is location. The Great Attractor sits behind the zone of avoidance. That's the region of space blocked by the Milky Way's disk. When you look in that direction, you're looking through the densest part of our own galaxy. All the stars, dust, and gas in the way block our view of what's beyond. It's like trying to see what's on the other side of a forest while standing in the middle of it. The trees are in the way. Astronomers have tried to look through the zone of avoidance using different wavelengths of light. Infrared can penetrate dust better than visible light. Radio waves can pass through even better, and they have found something. There's a massive concentration of galaxies in that direction. It's called the Norma cluster. It's definitely there, definitely massive, and definitely part of the Great Attractor's structure. But here's where it gets more complicated. As observations improved, astronomers realized the Norma cluster isn't massive enough. Even with all the galaxies they can detect in that region, there's not enough mass to explain the gravitational pull we're experiencing. Then in the 1990s, they discovered something even bigger. Beyond the Great Attractor, there's an even more massive structure called the Shapley supercluster. It's about 650 million light-years away, and it contains more than 8,000 galaxies. Some astronomers now think we're not being pulled by the Great Attractor alone. We might be being pulled by the combined gravity of the Great Attractor and the Shapley supercluster working together. But that's still not the full picture. In 2014, astronomers mapping the motions of galaxies across a huge volume of space discovered something they called Laniakea. That's Hawaiian for immeasurable heaven. Laniakea is a supercluster of galaxies that includes the Milky Way, the Virgo supercluster, the Great Attractor, and the Shapley supercluster. It contains about 100,000 galaxies spread across 520 million light-years. And here's what's fascinating. When you map out how galaxies move within Laniakea, they all flow toward a central point. That central point is the Great Attractor region. So in a sense, the Great Attractor isn't a single object. It's more like a gravitational basin at the center of our supercluster. All the matter in Laniakea is slowly flowing toward it. Think of it like a valley. If you pour water on a mountain, it flows downhill into the valley. The valley isn't pulling the water with some mysterious force. It's just the lowest point, and gravity naturally pulls everything toward it. The Great Attractor region is the lowest point in the gravitational landscape of our supercluster, and we're all flowing toward it. But even this explanation has complications. The zone of avoidance is still blocking our view. We can map the overall flow of galaxies, but we can't see exactly what's in that region. There might be even more massive galaxy clusters hidden behind our own galaxy's disk. Some estimates suggest there could be thousands of galaxies in the zone of avoidance that we simply haven't detected yet because of all the dust and stars in the way. Projects like the 2-micron all-sky survey have tried to penetrate the zone of avoidance using infrared light. They found hundreds of previously unknown galaxies, but infrared can only do so much. At some point, even infrared light gets blocked. Radio observations have helped too. The H.I. Park's all-sky survey mapped hydrogen gas throughout the region, revealing the distribution of galaxies we can't see optically. But we still don't have a complete picture. What makes the Great Attractor particularly strange is that we're inside the system. We're not observing it from the outside. We're part of it, being pulled by it, moving toward it. It's like being in a river. You can feel the current. You can measure how fast you're moving. But if the river disappears into fog downstream, you can't see where it's taking you. That's our situation. We know we're being pulled. We can measure our velocity. We can see some of the structure causing the pull. But the full picture is obscured. And here's something else to think about. This motion has been happening for billions of years. Long before humans existed, long before Earth formed, the matter that would eventually become our solar system was already moving toward the Great Attractor, and it'll keep happening for billions more years. Eventually, assuming the expansion of the universe doesn't interfere, the galaxies in our region of space will all collect near the Great Attractor. But we won't be around to see it. The timescales are too long. It would take hundreds of billions of years for this process to complete. Still, it's humbling to know that right now, as you're reading this, you're moving through space at 2.2 million kilometers per hour toward a gravitational anomaly we can barely see. The Great Attractor is out there, massive, pulling, hidden behind our own galaxy's glow. It's a reminder that even our cosmic neighborhood has mysteries we haven't fully solved. 2. Oumuamua. I already told you about Oumuamua in some detail earlier, but let me approach it from a different angle, because there's something about this object that bothers me more than anything else. It's the timing. Oumuamua was discovered on October 19th, 2017. The Pan-STARRS telescope in Hawaii caught it, and astronomers immediately knew it was special. Its trajectory showed it came from outside the solar system. It wasn't orbiting the sun. It was passing through. We had about 3 weeks to study it before it became too faint and distant to observe. 3 weeks. That's nothing. Think about what we've learned from other solar system objects. We've studied asteroids for centuries. We've sent spacecraft to comets, landed on them, analyzed their composition. We've had time. With Oumuamua, we got 3 weeks, and during those 3 weeks, we had to scramble to point every available telescope at it. Here's what kills me. Oumuamua probably wasn't the first interstellar object to pass through our solar system. Statistically, it can't have been. The galaxy is full of rogue asteroids and comets, ejected from other star systems. They must pass through our solar system occasionally. We just never noticed them before. Oumuamua was the first one we caught because our surveys got good enough. Pan-STARRS was designed to detect near-Earth asteroids, potential threats to our planet. It scans the sky repeatedly, looking for anything that moves. It happened to catch Oumuamua. But how many others did we miss? Some estimates suggest that at any given time, there might be several interstellar objects passing through the inner solar system. We just don't see them because they're faint and moving fast. Oumuamua got noticed because it passed relatively close to Earth, about 24 million kilometers at its nearest approach. That's close enough to get a decent look at it. But even then, it wasn't easy. Oumuamua is small, probably around 400 meters long and maybe 40 meters wide. That's tiny on cosmic scales, and it's dark. Its surface reflects only about 4% of the sunlight that hits it. A small, dark object moving fast through the solar system. It's amazing we saw it at all. Now let's talk about what made it weird. And I'm not even talking about the alien hypothesis yet. Just the basic observations were strange. First, the shape. Based on how its brightness changed as it tumbled, astronomers calculated it was extremely elongated. The estimates varied, but most suggested a length-to-width ratio of at least 10:1. That's unusual. Most asteroids are more irregular, lumpy. They're shaped like potatoes, not cigars. Some scientists suggested it might be more like a pancake, a flat disk rather than a cigar. The brightness variations could fit that too. But either way, it's an odd shape. Why would an interstellar asteroid be shaped like that? One possibility is that it's a fragment from a larger object. Maybe a planet in another star system was destroyed, and Oumuamua is a piece that got ejected. Fragments from collisions can have weird shapes. Another possibility is that it's not solid rock. Maybe it's more like a loosely bound collection of material held together weakly. Such objects can deform into elongated shapes. But we don't know. We couldn't get close enough to see details. Then there's the rotation. Oumuamua was tumbling as it moved through space. It rotated roughly every 7 to 8 hours. That's fast for an object its size. This kind of tumbling suggests it experienced some kind of violent event. Maybe a collision, maybe tidal forces from passing close to a star. Something gave it a spin. And here's the really weird part. Oumuamua didn't have a coma. Comets, when they get close to the sun, heat up. Ice on their surface vaporizes, creating a cloud of gas and dust. That's what makes comets visible and distinctive. Oumuamua passed well inside Mercury's orbit. It got close enough to the sun that if it had ice on its surface, we should have seen outgassing. We didn't. No coma. No tail. Nothing that suggested it was vaporizing. So maybe it's not a comet. Maybe it's more like an asteroid, made of rock or metal. That would explain the lack of outgassing. But then came the acceleration problem. After Oumuamua passed the sun and started heading back out of the solar system, astronomers tracked its trajectory carefully. They wanted to map exactly where it came from and where it was going. When they calculated its path using only gravity, the numbers didn't quite match the observations. Oumuamua was moving slightly faster than it should have been. It was accelerating away from the sun by a small amount that couldn't be explained by gravity alone. This is where things got really interesting. For comets, non-gravitational acceleration is normal. The gas, venting from their surface, creates a rocket effect, pushing them slightly. It's well understood and easy to calculate. But Oumuamua didn't have a visible coma. So what was pushing it? Scientists proposed several ideas. Maybe it was outgassing, but the gas wasn't carrying dust. If pure gas was venting from one side, it wouldn't create a visible coma, but it could still create thrust. Some observations hinted at very faint traces of hydrogen gas around Oumuamua, not enough to create a visible coma, but enough to cause the acceleration. The challenge is that this requires a very specific scenario. You need ice on the surface that's vaporizing, but it can't release dust, just pure gas. That's possible but unusual. Another idea involved radiation pressure. Sunlight carries momentum. When photons from the sun hit an object, they push it slightly. For most objects, this force is negligible compared to gravity. But if an object is very thin and light, radiation pressure can be significant. Maybe Oumuamua wasn't a cigar shape or a pancake. Maybe it was more like a sheet, a thin, flat object tumbling through space. If it was only a few meters thick, but hundreds of meters across, and if it was made of relatively low-density material, radiation pressure from the sun could explain the observed acceleration. But this raises questions. How would such an object form naturally? Why would it be so thin? This is where Abraham Loeb came in. Loeb is a respected astrophysicist at Harvard In 2018, he and his colleague Shmuel Bialy published a paper suggesting that Oumuamua might be artificial. Specifically, they proposed it could be a light sail, a thin reflective structure designed to be pushed by starlight. Such a sail could be a derelict spacecraft. Maybe it was built by an alien civilization millions of years ago, sent on some mission, and is now just drifting through space, broken or abandoned. Or maybe it's a probe, intentionally sent to explore other star systems. Maybe it's still functioning, observing as it passes through. This suggestion generated enormous controversy. Most astronomers were skeptical. The alien hypothesis is always the last resort. You exhaust all natural explanations first. And there were natural explanations for Oumuamua. They required some unusual conditions, but they were possible. Loeb argued that we should at least consider the possibility. If there's even a small chance Oumuamua was artificial, it would be the most important discovery in human history. But most scientists think the evidence doesn't support that conclusion. Oumuamua's properties can be explained naturally, even if the explanations are a bit stretched. Here's my take. Oumuamua was probably natural, probably a comet with unusual properties, or maybe a fragment from a destroyed planet in another star system. But the fact that we're even having this conversation tells you how weird it was. We've studied thousands of comets and asteroids in our solar system. Oumuamua was strange enough that serious scientists were willing to consider that it might be artificial. That alone makes it remarkable. And here's the frustrating part. We'll never know for sure. Oumuamua is gone. It's too far away and too faint to observe now. It's heading out of the solar system at about 26 kilometers per second relative to the Sun. In a few tens of thousands of years, it'll be in interstellar space, far from any star. We had one chance to study it, and we got 3 weeks. But the good news is, we're watching for more. Since Oumuamua, we've found other interstellar objects. In 2019, we detected 2I/Borisov, another interstellar visitor. Borisov was definitely a comet. It had a coma, a tail, and behaved exactly like comets in our solar system. It was unremarkable, which made it remarkable because it showed that interstellar comets are basically the same as solar system comets. Now that we know what to look for, we'll find more. The Vera C. Rubin Observatory, currently under construction in Chile, will scan the sky continuously once it's operational. It's expected to detect dozens or even hundreds of interstellar objects passing through our solar system each year. Each one will teach us something about planetary systems around other stars. Each one is a sample from somewhere else in the galaxy, delivered to us for free. And maybe, just maybe, one of them will be even stranger than Oumuamua. 3. Fast radio bursts, FRBs. In 2007, an astronomer named Duncan Lorimer was digging through old data from the Parkes Radio Telescope in Australia. He was looking at observations from 2001, 6 years earlier, trying to find pulsars. Pulsars are rotating neutron stars that emit beams of radio waves. As they spin, the beam sweeps across Earth like a lighthouse, creating regular pulses we can detect. Lorimer wasn't expecting to find anything unusual. He was just processing data. Then he saw something that made no sense. There was a pulse of radio energy in the data, but it wasn't from a pulsar. It was incredibly short, lasting only about 5 milliseconds. And it was powerful, really powerful. When Lorimer calculated the energy, he got a number that seemed impossible. In those 5 milliseconds, this thing had released as much energy as the sun emits in an entire day. And based on the signal's properties, it had come from far away, billions of light years. That meant the actual energy output was even more extreme. Something billions of light years away, producing a millisecond burst visible from Earth, must be unbelievably powerful. Lorimer published his finding in 2007. The burst became known as the Lorimer burst, and it was the first fast radio burst ever detected. At first, people were skeptical. A single anomalous signal in old data? Maybe it was interference. Maybe it was a glitch in the telescope. Maybe it was terrestrial noise that somehow got into the data. But then astronomers started finding more. As radio telescopes improved, and as astronomers specifically searched for these bursts, they started popping up. Not often, but regularly enough to confirm they were real. By 22,000, we've detected thousands of FRBs. They happen all the time, all across the sky. Estimates suggest that thousands of FRBs occur every day across the entire sky. We only detect a tiny fraction because we're not looking at the whole sky at once, and most FRBs are too faint or too far away to see. But here's what makes FRBs so strange. We still don't know what causes them. Let me describe what we've learned. FRBs are incredibly brief. Most last just a few milliseconds, though some are even shorter. The shortest detected FRBs last less than a millisecond. They're also incredibly energetic. The energy released in a typical FRB is equivalent to what the sun emits in weeks, months, or even years, all compressed into milliseconds. The strongest FRBs we've detected would be equivalent to 500 million suns, as you mentioned in the heading. How does something produce that much energy that quickly? FRBs come from distant galaxies, usually billions of light years away. We know this because of something called dispersion. As radio waves travel through space, they pass through gas and plasma. Different frequencies of radio waves travel at slightly different speeds through this material. Lower frequencies arrive slightly later than higher frequencies. By measuring this delay, astronomers can estimate how much gas the signal passed through, which tells them roughly how far away it came from. Most FRBs show dispersion consistent with cosmological distances. They're coming from other galaxies. Now, most FRBs are one-time events. They happen once and never repeat. You see a burst, you try to observe that same location again, and there's nothing. But some FRBs repeat. The first repeating FRB was discovered in 2016. It's called FRB 121-102. This source has produced hundreds of bursts over the years, allowing astronomers to study it in detail. The fact that some FRBs repeat is important. It tells us that whatever causes them doesn't destroy itself in the process. If FRBs were caused by some kind of catastrophic explosion, like a star exploding, you'd only get one burst. The source would be destroyed. But repeating FRBs prove that at least some sources can produce multiple bursts over time. This suggests that FRBs might not all have the same cause. Maybe there are different types. Maybe one-off FRBs are caused by catastrophic events, and repeating FRBs are caused by something else. Or maybe they're all caused by the same type of object, just under different conditions. What could produce an FRB? The leading theory involves magnetars. These are neutron stars with incredibly strong magnetic fields, the strongest magnetic fields in the known universe. Neutron stars are already extreme. They're the collapsed cores of massive stars, squeezed to incredible densities. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Magnetars take this extremity further. Their magnetic fields are thousands of times stronger than typical neutron stars. And sometimes, these magnetic fields become unstable. They can crack the neutron star's crust. They can cause starquakes. They can release enormous amounts of energy suddenly. It's thought that these magnetic field instabilities could produce FRBs. In 2000 and 2000, astronomers detected an FRB from within our own galaxy. This was huge. All previous FRBs had been cosmological, billions of light years away. But this one, FRB 200428, came from a known magnetar in the Milky Way called SGR 1935 plus 2154, located about 30,000 light-years away. The magnetar had been active, producing X-ray and gamma-ray bursts. Then, on April 28, 2020, it produced a radio burst consistent with an FRB. This was the first direct evidence linking FRBs to magnetars. It didn't prove all FRBs come from magnetars, but it showed magnetars can definitely produce them. Still, there are complications. The FRB from SGR 1935 plus 2154 was much weaker than the cosmological FRBs we detect. If that FRB had occurred in another galaxy billions of light-years away, we probably wouldn't have detected it. So, maybe magnetars can produce FRBs, but only the really powerful ones are visible at cosmological distances. Or maybe there are different mechanisms. Maybe magnetars produce some FRBs, and other sources produce others. Other theories for FRBs include collisions between neutron stars or black holes. The violent merger could release a burst of radio energy, supernova explosions, particularly unusual types that produce strong magnetic fields, pulsar-related phenomena. Maybe highly magnetized pulsars can produce bursts under certain conditions. Even more exotic ideas involve things like evaporating black holes or cosmic strings, hypothetical defects in space-time. But the magnetar theory is currently the frontrunner. Here's what bothers me about FRBs. They're happening constantly, thousands per day across the sky. That means the universe is full of sources capable of producing these incredible bursts of energy, and we only started noticing them in 2007. For all of human history up until then, FRBs were happening, and we had no idea. They were invisible to us because we didn't have the right instruments. Now we can see them, and they're everywhere. What else is out there that we just haven't noticed yet? FRBs also raise interesting possibilities for communication. Some people have speculated that advanced civilizations could use FRB-like signals to communicate across vast distances. If you can produce a burst of energy that's visible from billions of light-years away, that's a pretty good way to send a signal. But there's no evidence that any FRB is artificial. They all appear to be natural phenomena. Their properties are consistent with astrophysical processes, not engineered signals. Still, it's a reminder that the universe is capable of producing energy bursts that would be perfect for interstellar communication. Nature figured out how to do it naturally. As telescopes improve, we'll detect more FRBs. We'll locate them more precisely. We'll study the galaxies they come from. Each new FRB gives us more data. Each repeating FRB gives us a chance to observe the same source multiple times. Slowly, we're building up a picture of what causes these bursts. But for now, FRBs remain one of the most energetic, powerful, and poorly understood phenomena in the universe. Millisecond bursts of energy equivalent to millions of suns coming from across the cosmos, caused by something we're only beginning to understand. 4. The Boötes Voidi. I've talked about the Boötes Void before, but let me tell you what really gets me about it. It's not just that it's empty. It's how empty it is compared to what should be there. The universe isn't distributed evenly. Galaxies cluster together along filaments, creating a cosmic web. Between these filaments are voids, regions with fewer galaxies. This structure is normal. It's predicted by our models of how the universe evolved. Gravity pulled matter together into dense regions, leaving voids in between. Most voids are tens of millions of light-years across and contain some galaxies, just fewer than average. The Boötes Void is different. It's 330 million light-years across. That's one of the largest known voids in the nearby universe. But size alone isn't what makes it special. It's the emptiness. Based on the average density of galaxies in the universe, a volume that size should contain about 2,000 galaxies. The Boötes Void contains about 60. That's a deficit of 97%. Almost everything that should be there is missing. When Robert Kirshner and his colleagues discovered it in 1981, They weren't sure it was real. They were mapping galaxy distributions and found this huge region with almost nothing in it. Initially, they thought maybe their survey had a problem. Maybe they missed galaxies because of observational limitations. But follow-up surveys confirmed it. The void is real. So where did the galaxies go? They didn't go anywhere. The void isn't empty because galaxies were removed. It's empty because galaxies never formed there in large numbers. Here's how voids form. In the early universe, matter was distributed almost uniformly, but there were tiny density variations, random fluctuations. Regions that were slightly denser had slightly more gravity, so they attracted more matter. Over time, these dense regions became denser. Regions that were slightly less dense lost matter to their surroundings. Over time, these regions became emptier. This process, acting over billions of years, created the cosmic web. Dense regions became filaments and clusters. Less dense regions became voids. The Boötes void started as a region that was slightly less dense than average. Over billions of years, it lost matter to surrounding regions, becoming progressively emptier. But the scale is what's remarkable. For a void this large and this empty to form, the initial density contrast must have been significant, and the void had to have enough time to evolve. It takes billions of years for voids to expand and empty out. Computer simulations of structure formation can reproduce voids similar to the Boötes void, but they're rare in the simulations. You have to run many simulations before one produces a void this extreme. That suggests the Boötes void is a rare statistical fluctuation. It's possible, but uncommon. Now, the void isn't completely empty. There are about 60 galaxies scattered throughout it, and those galaxies are weird. Some of them are forming stars at unusually high rates. They're more active than galaxies in denser environments. Why? One idea is isolation. In dense regions, galaxies interact constantly. They pull on each other gravitationally. Sometimes they collide and merge. They exchange gas. These interactions can trigger star formation, but they can also disrupt it. A close encounter with another galaxy can heat up gas, making it harder for stars to form. Or it can strip gas away entirely. Galaxies in voids don't have these interactions. They're alone. They evolve in isolation. Maybe this isolation allows them to retain more gas. Without other galaxies stripping it away, they have more fuel for star formation. Or maybe the lack of interactions means they evolve differently. Without mergers shaking them up, they develop differently. We're still figuring this out. Void galaxies are harder to study because they're rare and distant. But they give us a natural experiment, a chance to see how galaxies evolve without the crowding and interactions that affect galaxies in dense environments. There's another interesting aspect to the Boötes void. It's part of a larger structure. Recent surveys have found that the Boötes void isn't an isolated feature. It's connected to other voids, forming a larger underdense region. Some astronomers have suggested that the Boötes void might be part of a superp void, an even larger region of lower than average density. If that's true, it would push the boundaries of structure formation even further. Our models predict limits on how large structures can be. There's a maximum size for voids based on the age of the universe and the strength of gravity. The Boötes void is close to this limit. If it's part of something even larger, that becomes problematic. But the data is still uncertain. We need better surveys to map the full extent of underdense regions around the Boötes void. Here's what fascinates me about voids in general. They're defined by what's not there. Most of astronomy is about observing things. Stars, galaxies, nebulae, black holes. We point telescopes at bright objects and study them. But voids are different. They're regions where there's almost nothing to observe. They're defined by absence. And yet, they're just as important for understanding the universe as the bright, dense regions. The distribution of voids tells us about the initial conditions of the universe. It tells us how matter was distributed in the early stages. It also tells us about dark matter and dark energy. These mysterious components make up most of the universe's mass and energy, and they play a crucial role in structure formation. Dark matter provides the gravitational scaffolding that allows normal matter to collect into galaxies and clusters. Dark energy drives the accelerating expansion of the universe, affecting how structures grow over time. By studying voids, their sizes, shapes, and evolution, we can constrain the properties of dark matter and dark energy. The Boötes void, as an extreme example, is particularly valuable for this. If our cosmological model is correct, voids like the Boötes void should be rare but possible. Finding them confirms that our models can produce these extreme structures. If we found voids much larger or emptier than the Boötes void, that would be a problem. It would suggest our models are missing something. So far, the Boötes void fits within theoretical limits, but just barely, and that makes it a useful test case. As surveys improve, we'll find more voids. We'll map their properties in greater detail. We'll compare them to simulations. Each one teaches us something about how the universe evolved from a nearly uniform state 13.8 billion years ago to the complex web of structure we see today. The Boötes void is a reminder that emptiness is just as much a part of the universe's structure as the bright galaxies and clusters. And understanding that emptiness is essential to understanding the cosmos as a whole. 5. Hypervelocity stars. In 2005, astronomers discovered a star that was moving wrong. Most stars in the Milky Way orbit the galactic center in relatively predictable paths. They move at a few hundred kilometers per second, held in orbit by the galaxy's gravity. This star, called SDSS J09 0745 0 plus 0 24 507, was moving at over 850 kilometers per second. That's fast enough to escape the Milky Way's gravity entirely. The star wasn't orbiting. It was leaving. They called it a hypervelocity star. Since then, astronomers have found more. As of 2205, we've identified several dozen hypervelocity stars, and each one raises the same question. What launched them? To understand why hypervelocity stars are strange, you need to understand escape velocity. Every object with mass has an escape velocity. That's the minimum speed you need to escape its gravitational pull completely. For Earth, escape velocity is about 11 kilometers per second. Rockets need to reach this speed to leave Earth and travel to other planets. For the Milky Way, escape velocity depends on where you are. Near the galactic center, it's higher. Out in the disk where we are, it's lower. But roughly, you need to be moving at 500 to 600 kilometers per second to escape the Milky Way from our location. Most stars move at 200 to 300 kilometers per second. They're safely bound to the galaxy. Hypervelocity stars move at 1,000 kilometers per second or more, some even faster. They're moving fast enough not just to escape the Milky Way, but to do so decisively. They're not barely escaping. They're being launched. So, what could accelerate a star to such extreme speeds? The leading theory involves the supermassive black hole at the center of the Milky Way. Our galaxy has a black hole at its core called Sagittarius A. It's about 4 million times the mass of the Sun. Black holes that massive have incredibly strong gravitational fields. And when you get close to them, strange things can happen. Here's the scenario. Imagine a binary star system, two stars orbiting each other. This binary happens to wander close to Sagittarius A. As they approach, the black hole's gravity starts to pull on both stars, but because they're in orbit around each other, their positions relative to the black hole are constantly changing. In some configurations, the black hole's gravity can transfer energy between the two stars. One star loses energy, and gets captured by the black hole. The other star gains energy and gets flung outward at incredible speed. This is called the Hills mechanism, named after astrophysicist Jack Hills, who proposed it in 1988. It's like a gravitational slingshot. The black hole's gravity tears apart the binary and launches one star away at hypervelocity. Computer simulations show this mechanism works. If you simulate binary stars passing close to a supermassive black hole, you can produce hypervelocity stars with the right properties, and observations support it. Many hypervelocity stars, when you trace their trajectories backward, appear to have originated from the galactic center. They're coming from the direction of Sagittarius A, but not all hypervelocity stars fit this picture. Some appear to have originated from other parts of the galaxy, not the center. Maybe there are other mechanisms that can accelerate stars to hypervelocity. One possibility involves supernova explosions in binary systems. Imagine two stars orbiting each other. One is massive and evolves faster. Eventually, it explodes as a supernova. The explosion is asymmetric, producing a kick that accelerates the neutron star or black hole remnant. This kick can be strong enough to unbind the binary. The companion star, suddenly released from its orbit, flies away at high speed, and the neutron star remnant gets kicked in the opposite direction. Under the right conditions, both objects can reach hypervelocity. This mechanism has been observed. We found neutron stars moving at hypervelocity, presumably kicked by asymmetric supernova explosions. So maybe some hypervelocity stars are the companions of exploded stars flung away by the blast. Another possibility involves interactions with intermediate mass black holes. These are black holes, larger than stellar mass black holes, but smaller than supermassive ones. They might exist in globular clusters or wandering through the galaxy. If a star has a close encounter with one of these black holes, it could get accelerated to hypervelocity through a similar mechanism to the Hills mechanism. But intermediate mass black holes are hypothetical. We've found candidates, but no definitive detections. So, this mechanism is more speculative. What fascinates me about hypervelocity stars is what they tell us about the galaxy's history. These stars were accelerated millions or even tens of millions of years ago. They've been traveling through space ever since, carrying information about the event that launched them. By studying their trajectories, we can learn about the conditions near the galactic center. We can test our models of how supermassive black holes interact with nearby stars. We can also learn about the structure of the Milky Way. As hypervelocity stars travel through the galaxy, their paths are affected by the galaxy's gravitational field. By measuring their positions and velocities precisely, we can map the distribution of mass in the Milky Way, including dark matter. Some hypervelocity stars are leaving the galaxy entirely. They'll eventually reach intergalactic space and drift through the void between galaxies. Imagine being on a planet orbiting one of these stars. Over millions of years, you'd watch the Milky Way shrink in the sky as you recede from it. Eventually, it would look like a distant spiral, one galaxy among billions. Your sky would be darker, with fewer stars. You'd be a wanderer, a star and its planets drifting through the cosmic void, unbound from any galaxy. There's something poetic about that. And here's a thought. If hypervelocity stars can escape the Milky Way, they can escape other galaxies too. That means intergalactic space might contain rogue stars, wandering between galaxies, orphans ejected from their home galaxies by close encounters with black holes or supernova kicks. We've actually detected some of these. They're called intra-cluster stars. They're found in galaxy clusters between the galaxies, not bound to any particular one. Some of them might be hypervelocity stars, ejected from their original galaxies. The universe is full of wanderers. Hypervelocity stars also raise an interesting question about habitability. If a star has planets, and that star gets ejected from the galaxy, what happens to the planets? Presumably, they stay with the star. Planets are bound to their star much more tightly than the star is bound to the galaxy. So you'd have a planetary system traveling through intergalactic space. The planets would still orbit their star. They'd still receive light and heat from it. Life could potentially exist on them if conditions were right. But they'd be isolated. No nearby stars. No galactic disk full of other stellar systems. If intelligent life existed on such a planet, their view of the universe would be very different from ours. They'd see a dark sky with just a few distant galaxies. They wouldn't have the rich star field we see in the Milky Way. Their astronomy would develop differently. They'd figure out galaxies early, because that's mostly what they'd see. It's a fascinating thought experiment. As our surveys improve, we're finding more hypervelocity stars. The Gaia satellite, which is mapping the positions and motions of over 1 billion stars, is particularly useful for this. Gaia measures how stars move across the sky with incredible precision. By analyzing its data, astronomers can identify stars with unusual velocities. We've found hundreds of candidates. Most need follow-up observations to confirm their truly hypervelocity, but the number is growing. Each new discovery helps us understand the mechanisms that produce them. And each one is a reminder that even stars, as massive and long-lived as they are, can be thrown around by the universe's more extreme forces. Supermassive black holes, supernova explosions, gravitational interactions. These processes can launch stars across the galaxy and beyond. Hypervelocity stars are proof that the universe plays rough. 6. The cold spot. I've mentioned the CMB cold spot before, but there's an angle I didn't fully explore. It's the statistical problem. The cosmic microwave background is the oldest light in the universe. It's been traveling toward us for 13.8 billion years, and it shows us what the universe looked like when it was just 380,000 years old. The CMB is remarkably uniform. The temperature is about 2.725 Kelvin in every direction, with tiny variations of about 1 part in 100,000. These tiny variations are the seeds of all structure in the universe. Regions that were slightly denser became galaxies and galaxy clusters. Regions that were slightly less dense became voids. So, the CMB is important. It's a map of the initial conditions. The cold spot is a region about 10 degrees across that's colder than it should be, about 70 millionths of a degree colder than the average. That doesn't sound like much, but in the context of the CMB's tiny variations, it's enormous. Here's the problem. Based on the standard model of cosmology, you can calculate the probability of such a large cold region appearing by random chance. The probability comes out to about 2%. Now, 2% isn't impossible. If you do 100 random experiments, you'd expect about 2 of them to produce a result this unlikely. But we only have one universe to observe. So, are we just unlucky? Did we happen to be in the 2% case? Or is the cold spot telling us something important? This is a question that has bothered cosmologists since the cold spot was first identified in 2004. Let me explain the options. Option 1. It's just a statistical fluke. The universe's initial conditions were random, governed by quantum fluctuations during inflation. By chance, this region happened to be a bit colder. This is the conservative explanation. It doesn't require new physics. It just requires accepting that unlikely things sometimes happen. Option 2. There's something in this direction causing the coldness. Maybe a supervoid. As I mentioned before, if photons from the CMB pass through a large void, they lose energy due to the integrated Sachs-Wolf effect. This would make that part of the CMB appear cooler. Astronomers have found evidence of a void in the direction of the cold spot. It's not as large as the Boötis void, but it's substantial. But calculations show that this void can only account for a small part of the cold spot's coldness, maybe 10 to 20%. To explain the full effect, you'd need a void much larger than what we observe. And we don't see evidence of such a large void. So the void explanation helps, but it doesn't fully solve the problem. Option 3. The cold spot is evidence of exotic physics. Maybe it's related to cosmic strings or domain walls, hypothetical defects in space-time predicted by some theories. Maybe it's evidence of a collision with another universe in a multiverse scenario. In some models of cosmic inflation, our universe is one bubble in a larger multiverse. If another bubble collided with ours in the early universe, it would leave a mark in the CMB, a circular region that's colder or warmer than average. The cold spot's shape is roughly consistent with this idea. It's somewhat circular, which is what you'd expect from a bubble collision. But this is highly speculative. We have no independent evidence for the multiverse beyond certain theoretical frameworks. So invoking a multiverse collision to explain the cold spot is a big leap. Option 4. There's an error in our observations or analysis. Maybe the cold spot isn't as significant as it appears. Maybe there's some systematic effect in the data that makes it look colder than it actually is. But the cold spot has been confirmed by multiple satellites. WMAP saw it. Planck saw it. It's real. So an observational error seems unlikely. What bothers me about the cold spot is that it's right on the edge of being a serious problem. If the probability were 0.01%, we'd be very confident something unusual was going on. We'd demand an explanation beyond chance. If the probability were 20%, we'd shrug it off as an expected fluctuation. But 2% is right in the middle. It's unlikely enough to be suspicious, but not so unlikely that we can rule out chance. This puts cosmologists in an uncomfortable position. Do we take the cold spot seriously as an anomaly, or do we dismiss it as bad luck? Different scientists have different opinions. Some think it's genuinely anomalous and points to new physics or unusual structure. Others think it's just an unlucky fluctuation, and we should expect to see a few unlikely features in the CMB just by chance. There's no consensus. And here's the frustrating part. We can't resolve this by making more observations of the CMB. We only have one CMB, one universe, one set of initial conditions. We can't run the experiment again to see if the cold spot appears in other universes. So we're stuck with the data we have. The only way forward is to look for other evidence. If the cold spot is caused by a supervoid, we should be able to map that void in detail and show it's large enough to explain the effect. If it's caused by exotic physics, maybe there are other signatures in the CMB or other observations that would support that. If it's caused by a multiverse collision, maybe there are other features we can look for that would be consistent with that scenario. But so far, none of these approaches has given a definitive answer. The cold spot remains ambiguous. Here's another angle. The CMB has other anomalies besides the cold spot. There's something called the axis of evil, a strange alignment of large-scale temperature fluctuations that shouldn't be there. There's a hemispherical asymmetry, where one half of the sky has slightly different statistical properties than the other half. These anomalies are also statistically unlikely, though not as extreme as the cold spot. Taken together, some cosmologists think the CMB is telling us that the standard model of cosmology is incomplete. Maybe the universe isn't as uniform as we thought. Maybe the initial conditions had some large-scale structure that our models don't account for. Or maybe we're just seeing noise. When you look at a complex dataset like the CMB, you'll find patterns. Some of them are meaningful. Some are just coincidence. Humans are pattern-seeking creatures. We see faces in clouds. We see constellations in random star patterns. Maybe we're seeing patterns in the CMB that aren't really there. The challenge is figuring out which anomalies are real and which are illusions. The cold spot is persistent. It's been seen by multiple instruments. It's in the data, but whether it means something or is just a fluke, we don't know. And that uncertainty is uncomfortable. Science likes clear answers. We like to say, this is what's happening and here's why. The cold spot doesn't let us do that. It's ambiguous, it's on the edge. And it's a reminder that even with some of the best data in cosmology, the CMB, we can still have mysteries we can't fully resolve. 7. Tabby's star. Let me come at Tabby's star from a different direction than before. I want to talk about what it felt like when this was discovered. In 2015, the Planet Hunters project posted data from Kepler for citizen scientists to analyze. Regular people, not professional astronomers, could help search for exoplanets by looking at light curves from thousands of stars. A few volunteers noticed something weird about one star, KIC 846-2852. The light curve showed irregular dips. Not the regular, periodic dips you'd expect from a planet, but chaotic, unpredictable dimming. They flagged it for professional astronomers to look at. Tabitha Boyajian, an astronomer at Yale at the time, led the team that investigated. When they analyzed the data carefully, they were baffled. This star dimmed by amounts that didn't make sense, up to 22% in some cases. No planet could do that. Jupiter, the largest planet in our solar system, only blocks about 1% of the sun's light when it passes in front. To block 22%, you'd need something massive, something planet-sized, but not a planet. The team wrote a paper describing the observations and proposing several explanations. Maybe a swarm of comets, maybe debris from a collision, but none of the explanations quite fit. Then a journalist asked Boyajian about the alien megastructure hypothesis. Was that possible? Boyajian said it was extremely unlikely, but they couldn't completely rule it out. That comment exploded into headlines. Suddenly, Tabby's star was everywhere. Alien megastructure found. Has Kepler discovered an alien civilization? The public excitement was intense. But here's what I find interesting. The professional astronomical community was more cautious. Most astronomers didn't think it was aliens. The alien hypothesis was always the least likely explanation, but they couldn't explain what it was. And that's rare. Usually, when we see something weird, we have a decent natural explanation. Maybe not proven, but plausible. With Tabby's star, every natural explanation had problems. Comets? Maybe, but you'd need an enormous number of them, and the timing seemed off. Debris? Maybe. But where's the infrared excess you'd expect from warm dust? Intrinsic variability. The star doesn't match known types of variable stars. Each explanation could account for some of the observations, but not all. So astronomers were in an uncomfortable position. They had observations that didn't fit any known phenomenon. And when that happens, you have to consider all possibilities, even unlikely ones. The alien megastructure hypothesis was proposed seriously by a few scientists, including Jason Wright at Penn State. Wright pointed out that an advanced civilization might build structures around their star to capture energy, a Dyson swarm. If such a structure were being built, it might block varying amounts of starlight as the components orbited. It would look irregular, unpredictable. It would look like Tabby's star. Now, Wright was careful. He didn't say it definitely was aliens. He said it was worth considering and worth investigating further. And investigating is exactly what happened. Astronomers organized campaigns to monitor Tabby's star continuously. If it dimmed again, they wanted to catch it in real time and observe it across multiple wavelengths. In 2017, it dimmed again. Telescopes around the world turned toward it. What they found was important. The dimming was more pronounced in blue light than in red light. This is called wavelength-dependent dimming, and it's consistent with dust. Small dust particles scatter blue light more effectively than red light. It's the same reason Earth's sky is blue. If dust was blocking the starlight, you'd expect blue light to be affected more than red. And that's what they saw. So probably not a solid structure. Probably dust. But that just pushes the question back. Where's the dust coming from? The latest thinking is that there might be a large cloud of dust orbiting the star, maybe from a destroyed planet or a collision or some other event. This dust cloud blocks light irregularly as it orbits. The problem is, we don't see the infrared excess we'd expect from dust warmed by the star's light. Maybe the dust is far from the star, so it's not heated much. Or maybe it's a specific type of dust that doesn't radiate efficiently in infrared. These explanations work, but they're a bit strained. Here's what I think is really going on. Tabby's star is probably natural, probably some kind of dust or debris phenomenon we don't fully understand. But the fact that we're still not certain, even after years of observations, tells you how weird this star is. Out of hundreds of billions of stars, this is the only one that behaves like this. That alone makes it remarkable. And it's a reminder that the universe still has surprises. We've studied stars for centuries. We have detailed models of how they work. We've classified thousands of different types. But then along comes one star that doesn't fit any category. It's humbling, and it's exciting because it means there are still things to learn. We haven't figured out everything about stars, even though we've been studying them for so long. Tabby's star is still being monitored. It's still dimming irregularly. Maybe one day we'll have enough data to definitively explain what's causing it. Or maybe it'll remain a mystery, a strange outlier that reminds us how much we don't know. 8. Haumea's ring. In 2017, astronomers detected something they didn't think was possible. They were observing a dwarf planet called Haumea, located in the Kuiper belt beyond Neptune. Haumea is weird on its own. It's shaped like a football, spinning so fast that it's been stretched into an elongated ellipsoid. It rotates once every 4 hours, which is incredibly fast for an object that size. But the 2017 discovery made it even stranger. Haumea has a ring. That might not sound shocking. Saturn has rings. Jupiter, Uranus, and Neptune all have rings. Rings are common around giant planets, but Haumea isn't a giant planet. It's a dwarf planet, small, only about 2,000 kilometers across at its longest dimension, and it's way out in the Kuiper belt, far from the Sun. Before 2017, no small body in the outer solar system was known to have a ring. The discovery was made using a technique called stellar occultation. When a distant object passes in front of a star from our perspective, the star briefly disappears. By measuring how long it takes for the star to reappear, you can learn about the object's size and shape. Astronomers predicted that Haumea would pass in front of a star on January 21st, 2017. They set up telescopes across Europe and South America to observe the event. As expected, the star dimmed when Haumea passed in front of it. But unexpectedly, the star also dimmed briefly a few seconds before and after the main event. These extra dips were short and symmetric. They looked like something else was blocking the star. When the astronomers analyzed the data, they realized Haumea had a ring. The ring was about 70 kilometers wide and located about 2,300 kilometers from Haumea's center. It's very thin, probably only a few kilometers thick at most, and it's almost perfectly circular, aligned with Haumea's equator. This raises a lot of questions. First, how did the ring form? For giant planets, rings usually come from destroyed moons. A moon wanders too close to the planet, tidal forces tear it apart, and the debris forms a ring. But Haumea is tiny compared to Saturn or Jupiter. Its gravity is much weaker. It's hard to imagine tidal forces strong enough to destroy a moon around such a small body. Another possibility is that the ring came from a collision. If another object smashed into Haumea, the debris could have formed a ring. Haumea already shows signs of a violent past. Its rapid rotation and elongated shape suggest it experienced a major impact at some point. Maybe that same impact created the ring. But if the ring came from a collision, why is it so thin and circular? Collision debris usually spreads out. It forms a cloud or disk that's messy and diffuse. Haumea's ring is narrow and well-defined. That suggests it's been shaped somehow. Maybe by gravitational interactions with Haumea's moons. Haumea has two known moons, Hyakka and Namaka. Maybe these moons' gravity shepherds the ring particles, keeping them confined to a narrow band. This happens with Saturn's rings. Some of Saturn's moons act as shepherds, keeping certain rings from spreading out. But Haumea's moons are small and far away. It's unclear if they could have this effect. Another mystery is why the ring is stable. Rings around planets are usually inside the Roche limit. That's the distance within which tidal forces from the planet are stronger than the object's own gravity. Inside the Roche limit, objects can't hold themselves together. They get torn apart. That's why rings exist. The material wants to coalesce into a moon, but tidal forces prevent it. Haumea's ring is outside the Roche limit. That means the particles in the ring should be able to stick together. Over time, they should clump into larger objects, eventually forming a moon. But the ring is still there. It hasn't coalesced. Why? Maybe the ring is young. Maybe it formed recently from a collision, and there hasn't been enough time for it to clump together yet. Or maybe something is preventing the particles from sticking. Maybe they're coated in ice, and collisions between them are more likely to shatter them than stick them together. We don't know. Haumea's ring also raises questions about other small bodies. If Haumea can have a ring, maybe other dwarf planets or large asteroids can too. In fact, since Haumea's discovery, astronomers have found rings around other small bodies. In 2014, they found rings around an asteroid called Chariklo. That was the first ring system discovered around a small body. Then they found rings around another small body called Chiron. So rings around small objects aren't as rare as we thought. But they're still unusual, and we don't fully understand how they form or why they're stable. Haumea's ring is particularly puzzling because of Haumea's unique properties: the rapid rotation, the elongated shape, the ring. All of these suggest a violent, complex history. Something happened to Haumea. Maybe a collision, maybe a near miss with another large object, something energetic that left it spinning fast, stretched into a football shape with a ring around it. Understanding what happened requires more observations. We need to study Haumea in more detail. Map its surface. Look for signs of impact craters or compositional differences. We need to observe its moons and understand their orbits and properties. And we need to study the ring itself. How dense is it? What are the particles made of? How are they distributed? Right now, our knowledge of Haumea comes mostly from Earth-based observations, telescopes looking at it from 1 billion kilometers away. A spacecraft mission to Haumea would reveal so much more. But missions to the outer solar system are expensive and take decades. A mission to Haumea isn't currently planned. So for now, Haumea's ring remains a mystery, a thin band of particles orbiting a rapidly spinning football-shaped dwarf planet in the frigid outer reaches of the solar system. It's strange, and it's a reminder that even in our own cosmic backyard, there are things we don't fully understand. 9. The hexagon on Saturn. In 1980 and 1981, the Voyager spacecraft flew past Saturn. They sent back stunning images of the planet's rings, its moons, and its atmosphere. Buried in that data was something bizarre. At Saturn's North Pole, there was a hexagon. Not a rough hexagon, not something that kind of looked hexagonal if you squinted. A nearly perfect hexagon. A six-sided shape with straight edges and sharp corners. It was a storm system, a massive, swirling cloud pattern. But instead of being circular like hurricanes on Earth, it was hexagonal. Each side of the hexagon is about 13,800 kilometers long. That's wider than Earth's diameter. The hexagon rotates with Saturn's interior, completing one rotation every 10 hours and 39 minutes. That's Saturn's rotation period. So, the hexagon is locked to the planet's rotation somehow. When Voyager first imaged it, scientists weren't sure it was real. Maybe it was a processing artifact. Maybe it was a temporary feature that would disappear. But in 2004, the Cassini spacecraft arrived at Saturn. It carried more advanced instruments, and the hexagon was still there. Cassini monitored Saturn for over 13 years, until 2017. Throughout that entire time, the hexagon persisted. It's been continuously observed for decades now. It's not going away. So what is it? The hexagon is a jet stream, a high-speed wind pattern in Saturn's upper atmosphere. On Earth, we have jet streams too. They're bands of fast-moving air in the upper atmosphere that flow west to east. Saturn has multiple jet streams at different latitudes, but the one at the North Pole has formed into this weird hexagonal shape. Why? Honestly, we're not entirely sure. Fluid dynamics is complicated. When you have a rotating sphere with an atmosphere, all sorts of complex flow patterns can emerge. On Earth, our jet streams are wavy. They meander north and south as they flow around the planet, but they don't form geometric shapes. Saturn's hexagon is different. The jet stream at the North Pole has somehow locked into a six-sided pattern. Scientists have created laboratory experiments and computer simulations to try to reproduce it. In 2010, a team in Spain managed to create a hexagonal flow pattern in a rotating tank of water. They had a cylindrical tank with water in it. At the center, they placed a small rotating cylinder. Around the edge, they spun the outer wall at a different speed. This created a flow pattern similar to Saturn's atmosphere, a fast-moving inner region and a slower-moving outer region. And under certain conditions, the boundary between these regions formed a polygon, sometimes a triangle, sometimes a square, sometimes a hexagon. The shape depended on the speed difference between the inner and outer regions, so the hexagon might be a natural consequence of the flow speeds in Saturn's atmosphere. The jet stream at the North Pole is moving at about 320 kilometers per hour. The surrounding atmosphere is moving slower. The boundary between these regions, where the speeds differ, forms the hexagon. But why a hexagon specifically? Why not a pentagon or a heptagon? That depends on the exact speed difference and other properties of the atmosphere. On Saturn, the conditions happen to produce a hexagon. If the speed difference was slightly different, it might be a different shape. It's worth noting that Saturn's south pole doesn't have a hexagon. It has a more typical circular vortex. So whatever conditions create the hexagon exist at the North Pole but not the South. This might be related to seasonal changes. Saturn has seasons, just like Earth, but they last much longer because Saturn's year is 29 Earth years. When Voyager visited in 1980, Saturn's North Pole was in winter, shrouded in darkness. When Cassini arrived in 2004, it was transitioning towards spring and summer. Cassini watched as the seasons changed. The lighting improved, allowing better views of the hexagon, and Cassini noticed changes. The hexagon's color shifted from blue to gold as summer approached. This color change is probably related to chemical reactions in the atmosphere driven by sunlight, but the hexagon's shape remained stable throughout. One of the most remarkable things about the hexagon is its longevity. Earth's weather patterns change constantly. Hurricanes last days or weeks. Jet streams shift positions seasonally. But Saturn's hexagon has been there for at least 40 years, probably longer. It's a semi-permanent feature of the planet's atmosphere. This tells us that Saturn's atmosphere is more stable than Earth's in some ways. Or maybe the hexagon is maintained by something deep inside the planet, some internal flow pattern that doesn't change much over time. Saturn is mostly gas. It doesn't have a solid surface. Its interior is layers of hydrogen and helium under increasing pressure and temperature. Deep inside, the hydrogen becomes metallic due to the extreme pressure. The planet's rotation creates flow patterns in these layers. Maybe the hexagon is connected to these deep flows. Maybe it's a surface expression of something happening far below. We don't know. Another interesting feature is that the hexagon has a circular storm at its center. Right at the North Pole, there's a hurricane-like vortex. It's about 2,000 kilometers across, with an eye about 50 kilometers in diameter. This polar vortex spins inside the hexagon. The relationship between the hexagon and the vortex isn't fully understood. Are they part of the same system? Does one cause the other? Or are they independent features that happen to coexist? More observations and simulations are needed to answer these questions. What I find fascinating about the hexagon is that nature can create such regular geometric shapes spontaneously. We tend to think of geometric shapes as artificial. Humans make hexagons. We build structures with straight edges and sharp corners. Nature is usually more chaotic, irregular. But here's a naturally occurring hexagon, thousands of kilometers across, persisting for decades. It's a reminder that nature follows mathematical laws. Fluid dynamics, governed by equations, can produce patterns that look designed, but are entirely natural. The hexagon isn't unique to Saturn. As I mentioned, laboratory experiments have produced similar patterns, and there might be hexagons on other planets. We just haven't observed them yet. Jupiter has complex atmospheric patterns. Maybe there are geometric shapes in its atmosphere we haven't noticed. Uranus and Neptune have jet streams and storm systems. Maybe they have polygonal features too. As our observations improve, we might find more of these strange geometric patterns. For now, Saturn's hexagon stands as one of the most visually striking and mysterious features in the solar system. A perfect geometric shape etched into the clouds of a giant planet rotating steadily, year after year. It's beautiful, and it's weird. 10. Fermi bubbles. In 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope found something enormous. Two giant structures extending above and below the center of the Milky Way. They called them the Fermi bubbles. Each bubble is about 25,000 light-years tall. Together, they span about 50,000 light-years, roughly half the diameter of the entire Milky Way. And they're emitting gamma rays, high-energy light that's invisible to our eyes, but detectable by space telescopes like Fermi. The bubbles are roughly symmetrical. One extends north from the galactic center, the other south. They're roughly egg-shaped, or maybe more like hourglasses. And they're huge, absolutely massive. How did we not notice them before? The answer is that they're faint and diffuse. They're not bright, like a star or a nebula. They're a subtle glow in gamma rays. Fermi had to stare at the galactic center for years, accumulating data before the bubbles became visible in the images. Once they were found, astronomers started looking at other wavelengths to see if the bubbles were visible there too. And they were. The bubbles show up in radio waves, X-rays, and even microwaves. They'd been hiding in the data all along. People just hadn't recognized them as a coherent structure. So what are they? The leading theory is that they're the result of activity from the supermassive black hole at the center of the Milky Way. Right now, Sagittarius A is relatively quiet. It's not actively feeding. Not much material is falling into it. But that hasn't always been the case. In the past, maybe a few million years ago, Sagittarius A might have gone through an active phase. Maybe a cloud of gas fell toward it. Or maybe a star wandered too close and got torn apart. Whatever the trigger, material started falling into the black hole. As it fell, it heated up, forming an accretion disk. This disk would have been incredibly hot, emitting enormous amounts of energy. Some of that energy would have been channeled into jets, powerful beams of matter and energy, shooting out from the black hole's poles. These jets would have punched through the galactic disk and expanded into the space above and below the galaxy. Over time, they created the bubbles. The gamma rays we see now are from particles in the bubbles colliding with gas and radiation, producing high-energy photons. This scenario makes sense. We see similar structures around other galaxies with active black holes. Some galaxies have enormous jets and lobes extending far beyond the galaxy itself. These are usually galaxies with very active black holes, actively feeding on large amounts of material. The Milky Way's bubbles are smaller and fainter, consistent with a less dramatic outburst. But the evidence is mostly circumstantial. We can't directly observe what happened millions of years ago. Another theory involves massive star formation. The galactic center has a lot of star formation happening. Massive stars are being born in dense clouds of gas. These massive stars live fast and die young. When they explode as supernovae, they release enormous amounts of energy. If many supernovae go off in a relatively short time, they could collectively create a shockwave that expands outward, forming structures like the Fermi bubbles. This is called a galactic wind. Material from the galaxy's disk gets blown out into the halo by the collective energy of many supernovae. We see galactic winds in other galaxies, especially those with high rates of star formation. So maybe the Fermi bubbles are the result of a starburst event in the Milky Way's center. Both explanations are plausible, and they're not mutually exclusive. Maybe both processes contributed. What's clear is that something energetic happened at the galactic center relatively recently in cosmic terms, and it left behind these giant structures that are still glowing in gamma rays millions of years later. One interesting aspect of the Fermi bubbles is what they tell us about the Milky Way's history. We tend to think of our galaxy as relatively quiet. Compared to galaxies with active galactic nuclei, we are quiet. But the Fermi bubbles suggest that the Milky Way has had episodes of much higher activity. Maybe Sagittarius A goes through cycles, long periods of quiet interrupted by brief periods of intense feeding. Maybe the galaxy goes through cycles of star formation, quiet periods followed by bursts. The bubbles are evidence of one of these active periods. There's also a connection to something called the Erosita bubbles. In 2002, the EOROICIT X-ray telescope found similar structures in X-rays. They're roughly aligned with the Fermi bubbles, but extend even farther. This suggests the phenomenon is even larger and more complex than we initially thought. The multi-wavelength observations are helping us understand the structure and composition of the bubbles. Different wavelengths trace different physical processes. Gamma rays come from very high-energy particles. X-rays come from hot gas. Radio waves come from electrons spiraling in magnetic fields. By comparing observations at different wavelengths, we can build a more complete picture. What we're learning is that the bubbles are filled with gas that's hotter and more energetic than the surrounding galactic halo. They're also magnetized. There are magnetic fields threading through the bubbles, and there are cosmic rays, high-energy particles zipping through the structures. All of this is consistent with the bubbles being driven by energetic outflows from the galactic center. Here's what bothers me about the Fermi bubbles. They're enormous. They dominate the structure of the Milky Way's halo, and we only discovered them in 2010. That means for all of human history up until 14 years ago, we had no idea these giant structures existed above and below our galaxy. They were invisible to us because we couldn't detect gamma rays from the ground. We needed space telescopes. It makes you wonder what else is out there that we haven't detected yet. What other enormous structures are invisible to us because we don't have the right instruments, or we're not looking in the right way. The universe is full of things we can't see. Dark matter, dark energy, neutrinos, gravitational waves, before we detected them. Every time we develop a new way of observing the universe, we find something unexpected. The Fermi bubbles are a perfect example. They were always there. We just couldn't see them until we built a gamma-ray telescope and looked carefully enough. And now that we know they're there, we're learning that our galaxy is more dynamic, more active than we thought. It's not just a static collection of stars slowly orbiting. It's a living system with outflows, feedback, cycles of activity. The Fermi bubbles are part of that story. Two enormous structures filled with hot gas and cosmic rays, glowing in gamma rays, extending across half the galaxy. Evidence of some massive event millions of years ago that we're only now beginning to understand. 11. The wow. Signal. I've told you about the wow. Signal before, but there's something about it that haunts me more than anything else. It's the silence that followed. August 15th, 1977. The Big Ear radio telescope in Ohio picks up a signal. Jerry Amon sees it in the data, writes, "Wow," in red pen. And then, nothing. For almost 50 years, nothing. Let me put this in perspective. We've been searching for the wow, signal's source, for longer than most people's entire careers. Astronomers have pointed telescopes at that same patch of sky hundreds of times. They've used more sensitive equipment than the Big Ear. They've searched at the same frequency and nearby frequencies. Complete silence. Here's what bothers me about this. If it was a natural phenomenon, we should have seen it again. Natural sources tend to be repetitive, or at least consistent. Pulsars pulse regularly. Quasars emit continuously. Even transient events, like supernovae or gamma-ray bursts, have been seen multiple times across the universe. But the wow signal? Once, 72 seconds. Gone. If it was artificial, that's almost worse. Because then we have to ask, why would an alien civilization transmit once and never again? Think about our own attempts to communicate with potential aliens. We've sent messages like the Arecibo message in 1974. We've put plaques on spacecraft. We've considered building beacons that would transmit continuously or repeatedly. Why? Because a one-time message is nearly useless. The odds of anyone catching it are astronomically low. Space is huge. Even if you're broadcasting in all directions, the signal spreads out. It gets weaker. By the time it reaches another star system, it's incredibly faint. And the receiver needs to be listening at the exact right time, at the exact right frequency, in the exact right direction. The chances of catching a one-time transmission are essentially zero. We caught the wow signal. Against all odds, we happen to be listening to the right frequency, in the right direction, at the right time. What are the odds of that? Some people suggest it might have been a lighthouse strategy. Imagine a beam sweeping across the galaxy like a lighthouse beam sweeps across the ocean. We just happened to be in the beam's path for 72 seconds as it swept past Earth. That would explain why it never repeated. The beam moved on, and it won't come back around for a long time. Maybe years, maybe centuries. But even this explanation has problems. The wow signal's frequency was around 1,420 megahertz. That's the hydrogen line, a natural frequency that would be universally recognizable. It's a smart choice for interstellar communication. Any civilization that understands radio astronomy would recognize this frequency as significant. But here's the thing. The 1,420 megahertz band is protected by international agreement. We don't transmit at this frequency because it's reserved for radio astronomy. If aliens chose this frequency for the same reason we consider it important, they'd probably transmit multiple times or continuously. Why choose a universal frequency and then use it only once? It doesn't make sense, unless something went wrong. Maybe the transmission was interrupted. Maybe the civilization that sent it no longer exists. Or maybe it wasn't meant for us at all. Maybe it was a transmission between two other points, and we just happened to intercept it. Like picking up a phone conversation between two people who don't know you're listening. The signal wasn't directed at Earth. We just happened to be in the way. That would explain the one-time nature. They weren't trying to establish contact with us. We just accidentally eavesdropped on their communication. Now let me tell you about the comet theory, because this is where things get really frustrating. In 2016, a researcher named Antonio Paris proposed that the WOW signal might have been caused by comets, specifically two comets, 266P/Christensen and P2008Y2. These comets were in that region of sky in 1977, and comets can emit radio waves at the hydrogen line frequency. When the solar wind interacts with the hydrogen cloud around a comet, it can produce radio emissions. Paris's theory got a lot of media attention. Headlines proclaimed, "Wow, signal mystery solved." But here's the problem. The WOW signal was incredibly narrow band. It occupied a very specific frequency. Natural sources usually produce broad spectrum emissions. They emit across a range of frequencies. The narrowness of the WOW signal is more consistent with an artificial source, something deliberately transmitting on a chosen frequency. Comets produce broadband emissions. They don't produce narrowband signals like the WOW signal. When other scientists tested Paris's comet theory by observing these and other comets, they found that comets do emit at radio frequencies, but the signal characteristics don't match the WOW signal. So the comet explanation doesn't really work, but it's become part of the WOW signal's story. A lot of people think the mystery is solved, that it was just comets. It wasn't. The mystery remains. Here's another angle that doesn't get talked about enough. The Big Ear telescope had limitations. It couldn't pinpoint locations very precisely. It could tell you the general direction, but not the specific source. We know the WOW signal came from somewhere in the constellation Sagittarius, but that's a big area of sky. Thousands of stars. Even if we wanted to send a message back, we wouldn't know exactly where to aim. The Big Ear also had two receivers that scanned the same patch of sky 3 minutes apart. The WOW signal showed up on the first receiver, but not the second. This means it lasted less than 3 minutes. Probably the 72 seconds recorded, but maybe up to 3 minutes. Why would it turn off between the two scans? If it was a continuous transmission, both receivers should have detected it. If it was a pulse transmission, repeating regularly, both receivers should have caught it. The fact that it appeared once and not 3 minutes later is bizarre. It suggests the transmission was either very brief or very specific in timing. Let me tell you what I think is the most likely explanation, even though it's unsatisfying. The WOW signal was probably terrestrial interference. Some satellite, aircraft, or ground-based transmitter happened to send a signal at just the right moment. The Big Ear's filters and design were supposed to eliminate terrestrial interference, but maybe something slipped through. This explanation is boring. It's unsatisfying, but it's probably the most likely. The problem is, we can't prove it. We don't know what satellite or transmitter could have caused it. The signal characteristics don't match known sources of interference, so we're left with uncertainty. Maybe it was interference. Maybe it was a comet. Maybe it was an alien transmission. Maybe it was some natural phenomenon we don't understand yet. We'll probably never know. And that's what makes the WOW signal so frustrating and so compelling. It's a genuine mystery, a piece of data that doesn't fit any explanation perfectly. And it's a reminder of how difficult SETI is, the search for extraterrestrial intelligence. We've been listening to the sky for decades now. We've surveyed millions of stars. We've detected thousands of signals. But we've only found one that we can't explain. And even that one is ambiguous. If there are alien civilizations out there transmitting, either they're very rare, very quiet, or we're not looking in the right way. The WOW signal is our best candidate in nearly 50 years of searching. One ambiguous signal that lasted 72 seconds in 1977. That's it. The universe is either very empty or very good at keeping secrets. And somewhere in the direction of Sagittarius, something transmitted a powerful narrowband radio signal at the hydrogen line frequency, and we caught it for 72 seconds. What it was, we may never know, but it happened. The data is real. Jerry Amon saw it and wrote, "Wow," and that moment is frozen in time. A moment when we might have heard from something beyond Earth, or when we caught a glimpse of some natural phenomenon we don't understand. Either way, it's one of the strangest things we've ever detected, and the silence that followed is just as strange as the signal itself. 12. Magnetars. Let me tell you about the most powerful magnets in the universe. They're called magnetars, and they're terrifying. A magnetar is a type of neutron star. Neutron stars are already extreme. They're the collapsed cores of massive stars, squeezed down to about 20 kilometers in diameter. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. They're so dense that protons and electrons are crushed together into neutrons, hence the name. But magnetars take it further. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar's magnetic field is about 1,000 times stronger than that. We're talking about magnetic fields of 10 circumflex, 15 Gauss. That's 1 quadrillion times stronger than Earth's magnetic field. At that strength, the magnetic field does things that sound like science fiction. First, it warps atoms. The electron clouds around atoms get stretched into cigar shapes, aligned with the magnetic field. Chemistry as we know it doesn't work near a magnetar. Second, the magnetic field is so strong it affects the vacuum of space itself. In quantum mechanics, empty space isn't really empty. It's filled with virtual particles constantly popping in and out of existence. Near a magnetar, the magnetic field polarizes this quantum foam. It creates a kind of birefringence in the vacuum. Light traveling through this region gets affected. Different polarizations travel at different speeds. This is something that normally only happens in materials like crystals. But near a magnetar, the vacuum itself acts like a crystal. Third, if you got within 1,000 kilometers of a magnetar, the magnetic field would be lethal. It would interfere with the electrical signals in your nervous system. Your neurons couldn't fire properly. You'd lose consciousness instantly. You'd be dead before you even felt anything. But it gets worse. The magnetic field would also interact with the atoms in your body. At extreme field strengths, the atoms themselves get distorted. The chemical bonds that hold molecules together would be disrupted. You wouldn't just die. You'd essentially disintegrate at the molecular level. And here's the famous claim you mentioned in the heading. A magnetar's magnetic field is so strong that it could erase the magnetic strip on a credit card from halfway across the solar system. That's about 4 AU, or 600 million kilometers away. Now, to be clear, there are no magnetars anywhere near our solar system. The closest known magnetar is thousands of light years away. We're in no danger, but the fact that such extreme magnetic fields exist in nature is remarkable. How do magnetars form? They start as massive stars. When such a star runs out of fuel, its core collapses. The outer layers explode in a supernova, and the core gets compressed into a neutron star. Most neutron stars end up with strong magnetic fields, but magnetars are special. We think magnetars form from neutron stars that are born spinning very rapidly, maybe hundreds of times per second. The combination of rapid rotation and the dynamo effect in the neutron star's interior amplifies the magnetic field to extreme levels. It's similar to how Earth's magnetic field is generated by the motion of molten iron in the core, but on steroids. Once formed, the magnetar slowly loses energy. The intense magnetic field exerts a drag on the star's rotation, slowing it down over time. Young magnetars spin fast and have the strongest fields. Old magnetars spin slower and their fields have decayed somewhat. But even old magnetars have magnetic fields far stronger than any normal neutron star. Now here's where magnetars get really interesting. Sometimes the magnetic field becomes unstable. The neutron star's crust is solid, made of a lattice of atomic nuclei. But the interior is more fluid. The magnetic field threads through both regions. If the interior field shifts, it can stress the crust. Eventually, the crust cracks. When this happens, the magnetic field suddenly reconfigures. Energy that was stored in the field gets released explosively. This is called a magnetar flare. The energy released in a magnetar flare is staggering. In 2004, a magnetar called SGR 180620, located about 50,000 light-years away, produced a flare. For a fraction of a second, it was the brightest object in the sky outside the solar system. It briefly outshone the full moon, even though it was halfway across the galaxy. The energy released in that fraction of a second was more than the sun emits in 150,000 years. And this was from an object only 20 kilometers across. The flare also released a flood of gamma rays and X-rays. Satellites detected the burst. Earth's ionosphere was disturbed. If that magnetar had been 10 light-years away instead of 50,000, the radiation would have been intense enough to cause a mass extinction on Earth. Fortunately, there are no magnetars that close. Magnetar flares are thought to be the source of some fast radio bursts, which I talked about earlier. In 22, when the magnetar SGR 1935 plus 2154 flared, it produced a radio burst consistent with an FRB. This was the first direct evidence linking magnetars to FRBs. So magnetars aren't just extreme magnets. They're also sources of some of the most energetic transient events in the universe. Here's something that bothers me about magnetars. We've only known about them since the 1990s. Before then, we knew neutron stars existed. We discovered pulsars in the 1960s, and we understood they were rotating neutron stars. But we didn't know about magnetars. We didn't know neutron stars could have such extreme magnetic fields. The first magnetar candidates were detected as soft gamma repeaters, sources that would emit bursts of soft gamma rays irregularly. At first, astronomers didn't know what they were. They proposed various explanations. It wasn't until the 1990s that the magnetar model was developed by Robert Duncan and Christopher Thompson. They proposed that these soft gamma repeaters were neutron stars with ultra-strong magnetic fields. The bursts were caused by magnetic field reconfigurations and starquakes. This model explained the observations beautifully, and as more data came in, it became clear that magnetars were real. Now we've identified about 30 magnetars in our galaxy and nearby galaxies. That might not sound like many, but magnetars are rare. Most neutron stars don't become magnetars, and magnetars are short-lived, astronomically speaking. Their intense magnetic fields decay over tens of thousands of years. So, the magnetars we see today are young, born within the last few tens of thousands of years. Older magnetars fade and become indistinguishable from regular neutron stars. This means there could be many dead magnetars out there, former magnetars whose fields have decayed. We just can't identify them anymore because they're not actively flaring. One question that fascinates me: what would it be like to observe a magnetar up close? Obviously, you couldn't get close. The radiation and magnetic field would kill you. But hypothetically, from a safe distance, what would you see? The surface of a neutron star is incredibly hot, temperatures of millions of degrees. The intense magnetic field channels particles along field lines, creating hotspots at the magnetic poles. These hotspots emit X-rays and gamma rays. As the magnetar rotates, these hotspots swing in and out of view, creating pulses of radiation. That's how we detect many magnetars, by their pulsations. But unlike regular pulsars, which pulse very regularly, magnetars are erratic. They glitch. They flare. They change their rotation rate unpredictably. The magnetic field is so strong, it stresses the star's structure. The crust cracks. The field reconfigures. This creates an unstable, chaotic environment. Observing a magnetar would be like watching a cosmic time bomb. You'd never know when the next flare would erupt, and when it did, the energy release would be visible across the galaxy. Here's a final thought about magnetars. They represent one of the most extreme states of matter in the universe. Short of a black hole, there's nothing more extreme than the conditions in a magnetar. Density so high that atoms are crushed. Magnetic fields so strong they warp space and atoms. Rotation so fast that the surface moves at a significant fraction of the speed of light. Temperatures of millions of degrees. And all of this packed into a sphere 20 kilometers across. The physics in a magnetar is at the edge of what we understand. Quantum mechanics, general relativity, nuclear physics, electromagnetism, all pushed to their limits. Studying magnetars teaches us about physics in regimes we can never recreate on Earth. No laboratory can produce the conditions inside a magnetar, so we observe them from a distance and try to understand the data. And every flare, every pulse, every observation gives us a glimpse into one of the most extreme environments nature can create. Magnetars are proof that the universe is far more violent and extreme than everyday experience suggests. They're neutron stars on steroids, cosmic magnets, so powerful they could erase your credit card from 600 million kilometers away. They're terrifying and fascinating in equal measure. 13. The Pistol Star. In 1990, astronomers using infrared telescopes discovered a star near the center of the Milky Way that shouldn't be able to exist. They called it the Pistol Star because it's located near a nebula shaped like a pistol. The Pistol Star is a hypergiant, one of the most luminous stars ever discovered. It's about 25,000 light-years away, hidden behind dense clouds of dust near the galactic center. You can't see it with visible light. The dust absorbs it all. But in infrared, it shines through. And what astronomers found was shocking. The Pistol Star is putting out as much energy as 1.7 million suns. Let me put that in perspective. If you replace the sun with the Pistol Star, the Earth would be vaporized instantly. Actually, let's go further. If the Pistol Star were at the center of the solar system, you could place it at the distance of Uranus, about 1980 U from Earth. At that distance, it would still appear as bright as the sun does from Earth. That's how luminous it is. The Pistol Star is so bright that if you could see it from Earth without the dust in the way, it would be one of the brightest objects in the night sky, even from 25,000 light-years away. Now, you might wonder, if it's so bright, why haven't we heard about it more? The answer is that the Pistol Star is extremely rare, and it won't last long. Stars like this are so massive and so luminous that they burn through their fuel incredibly quickly. The Pistol Star is probably only a few million years old. That's nothing in cosmic time. The Sun is 4.6 billion years old and will live another 5 billion years. The Pistol Star will be dead in another few million years at most. It's living fast and dying young. Here's the thing about very massive stars. There's a theoretical limit called the Eddington limit. When a star is massive and luminous enough, the radiation pressure pushing outward becomes so strong it can overcome gravity pulling inward. If a star exceeds the Eddington limit, it starts blowing itself apart. The Pistol Star is right at this limit, maybe even exceeding it. It's so luminous that its radiation pressure is actively expelling its outer layers, and we can see the evidence. The Pistol Star is surrounded by the Pistol Nebula, a cloud of gas and dust that the star has ejected. The nebula contains about 10 times the mass of the Sun. That's material that used to be part of the Pistol Star, but was blown away by the star's intense radiation. The star is literally shedding mass to avoid tearing itself apart. Over its lifetime, the pistol star might have lost 50 to 100 times the Sun's mass. It's thought the star originally formed with well over 100 solar masses. Now it's down to maybe 80 or 90 solar masses, and it's still losing mass. Stars this massive are incredibly rare. In the entire Milky Way, there might only be a few dozen stars as luminous as the pistol star. Why are they so rare? First, forming such a massive star requires special conditions. You need a dense cloud of gas and just the right collapse dynamics. Most stellar nurseries produce a range of star masses, with smaller stars being far more common. Very massive stars are statistical outliers. Second, massive stars don't live long. They burn through their fuel in just a few million years. So even if they form, they don't stick around. At any given time, there are only a few of them in the galaxy. By contrast, there are hundreds of billions of low-mass stars like the Sun that can live for tens of billions of years. The pistol star is also a variable star. Its brightness changes over time. This is common for hypergiants. They're unstable. The intense radiation pressure creates instabilities in the star's outer layers. Material flows outward, then falls back. The star pulsates. This creates variations in brightness. Monitoring these variations helps astronomers understand what's happening in the star's outer atmosphere. Now, what's the pistol star's fate? Stars this massive end their lives in spectacular supernova explosions. When the pistol star exhausts its nuclear fuel, its core will collapse. The result will be either a neutron star or a black hole, depending on exactly how massive the core is. And the explosion will be visible across the galaxy. For a brief time, the supernova might outshine billions of stars. If it happened today, we'd see it as a bright new star appearing in the sky, visible even in daylight. But today is relative. The pistol star is 25,000 light-years away. If it exploded today, we wouldn't see it for another 25,000 years. For all we know, it might have already exploded. The light just hasn't reached us yet. Or it might explode tomorrow, or in a million years. We don't know. What we do know is that the pistol star is one of the most extreme stars in the galaxy. It's a testament to how violent and energetic stellar physics can be. Most stars, like the Sun, live quiet, stable lives. They fuse hydrogen into helium for billions of years, barely changing. But stars like the pistol star are different. They're chaotic, violent, unstable. They blow away their own mass. They vary in brightness. They push the limits of what's physically possible, and they remind us that the universe creates extremes, not just black holes and magnetars, but also stars so luminous they would outshine the Sun from billions of kilometers away. The pistol star is a monster, a hypergiant burning with the fury of 1.7 million suns. And somewhere near the center of our galaxy, it's shining right now, hidden behind dust, slowly tearing itself apart. 14. Dark Flow. In 2008, a team of astronomers led by Alexander Kashlinsky made an announcement that bothered a lot of cosmologists. They'd been studying the motion of galaxy clusters using data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP. What they found was unexpected. Galaxy clusters across a huge region of the sky were all moving in the same direction, not just drifting randomly, moving together in a coordinated flow toward a specific point in space. They called it dark flow. Now, this is weird. Let me explain why. The universe is expanding. Space itself is stretching, carrying galaxies apart. On large scales, galaxies should be moving away from each other due to this expansion. On smaller scales, galaxies can have their own individual motions. They orbit within clusters. Clusters can move toward each other if they're gravitationally bound. But what Kashlinski's team found was different. They weren't looking at individual galaxy motions. They were looking at the large-scale flow of hundreds of galaxy clusters. And these clusters, spanning billions of light-years, all seem to be flowing in the same direction at about 600 to 1,000 kilometers per second. That's fast, and it's coordinated. This contradicts what we expect from the standard cosmological model. According to the cosmological principle, the universe should be homogeneous and isotropic on large scales. That means matter should be distributed roughly evenly, and there shouldn't be preferred directions. But dark flow suggests there is a preferred direction, a large-scale structure, or gravitational influence pulling galaxy clusters in a specific direction. Where are they flowing toward? The direction is roughly toward the constellation Centaurus and Hydra. Some researchers have called this region the Great Attractor area, though it's not the same as the Great Attractor I talked about earlier. It's more like the galaxy clusters are flowing towards something beyond the Great Attractor. So what could cause this? One possibility is that there's an enormous concentration of mass outside our observable universe. Remember, the observable universe is finite. There's a horizon beyond which we can't see because light hasn't had time to reach us yet. But just because we can't see beyond that horizon doesn't mean there's nothing there. If there's a massive structure, a supercluster or collection of superclusters just beyond our observable horizon, its gravity could still affect the matter within our observable universe. This would create a large-scale flow toward that structure. We couldn't see the structure directly, but we'd see its gravitational influence. This is one explanation for dark flow. But it's troubling because it suggests the universe beyond our horizon is not uniform. There's some huge mass concentration out there that we can't see, but that's affecting everything we can see. Another possibility is that dark flow is a remnant of the early universe. In the first moments after the Big Bang, before inflation, the universe might have had some large-scale structure or anisotropy. Inflation is thought to have smoothed out most irregularities, but maybe not all. Maybe some large-scale flows survived inflation and are still observable today as dark flow. This is speculative, but it's possible. A third possibility is that dark flow doesn't exist. When Kashlinski's team announced their findings, other astronomers were skeptical. Measuring large-scale flows is difficult. You have to separate the motion due to the universe's expansion from the peculiar motion of galaxies. You also have to account for various systematic effects in the data. Some researchers have reanalyzed the data and claimed they don't see dark flow. They argue that the effect is an artifact of the analysis, not a real phenomenon. This debate has continued for years. Data from the Planck satellite, which mapped the cosmic microwave background with higher precision than WMAP, has been used to test for dark flow. Some analyses of Planck data find weak evidence for it. Others find no evidence. The jury is still out. Here's what bothers me about dark flow. If it's real, it's a major challenge to the standard cosmological model. The cosmological principle is fundamental to our understanding of the universe. It's built into the equations of general relativity that we use to model the universe's evolution. If the universe has large-scale flows that violate this principle, we need to rethink our models. That doesn't mean the Big Bang is wrong. It means our models might be incomplete. Maybe the universe is lumpier at large scales than we thought. Maybe there are structures beyond our horizon that we need to account for. Or maybe dark flow is telling us something about the initial conditions of the universe. Some versions of cosmic inflation predict that the universe could have large-scale flows or anisotropies. If dark flow is real, it might be evidence for specific inflation models. But if dark flow isn't real, if it's just a data analysis issue, then we can breathe easier. The cosmological principle holds. The universe is homogeneous and isotropic as we thought. No need to revise our models. The problem is, We don't know which scenario is true yet. The data is ambiguous. Different analyses give different results. We need better observations to settle this. Future surveys of galaxy clusters, combined with better cosmic microwave background data, might resolve the question. Until then, dark flow remains a controversial and unresolved issue in cosmology. It's a reminder that even our most fundamental assumptions about the universe, like the cosmological principle, are based on observations. And if new observations contradict those assumptions, we need to be willing to reconsider. That's how science works. We don't cling to ideas because they're comfortable. We follow the evidence wherever it leads. If the evidence says there's a large-scale flow of galaxy clusters towards some distant mass concentration, then we need to take that seriously, even if it challenges our models, even if it suggests the universe is stranger and less symmetric than we hoped. For now, dark flow is a question mark, a possible large-scale motion of galaxy clusters that might or might not be real. If it's real, it's one of the strangest things we've discovered about the universe's large-scale structure. If it's not, it's a cautionary tale about the difficulty of cosmological observations and data analysis. Either way, it's a reminder that we're still figuring out how the universe works on the largest scales, and there are still surprises waiting. 15. Hyperion Saturn has over 80 moons. Most of them are small, irregular chunks of ice and rock, but one of them is truly bizarre. It's called Hyperion, and it's a moon that doesn't make sense. First, let's talk about its appearance. Hyperion looks like a sponge, or maybe a giant piece of pumice. Its surface is covered in craters, but not normal craters. These are deep, sharp-edged pits that give the moon a porous, sponge-like appearance. The craters don't have the usual smooth, degraded look you see on most moons. They look fresh, sharp, almost artificial. When the Cassini spacecraft flew by Hyperion and sent back detailed images, scientists were stunned. Nobody expected a moon to look like this. The sponge-like appearance is probably related to Hyperion's density. It's one of the least dense objects in the solar system. Its density is about 0.5 grams per cubic centimeter. That's half the density of water. If you could find an ocean big enough, Hyperion would float. This low density means Hyperion is extremely porous. It's more empty space than solid material. Probably about 40% of Hyperion's volume is empty space. It's like a pile of rubble loosely held together by gravity. When meteorites hit this porous surface, they create those sharp, deep craters instead of the usual bowl-shaped ones. The material doesn't compress and flow like it would on a solid surface. It just collapses into the void below. So you get these strange geometric pits. But Hyperion's weirdness doesn't stop with its appearance. Its rotation is completely chaotic. Let me explain what I mean by that. Most moons in the solar system are tidally locked to their parent planet. This means they always show the same face to the planet. Earth's moon does this. One side always faces Earth. The other side, the far side, always faces away. This happens because of tidal forces. Over time, the planet's gravity synchronizes the moon's rotation with its orbit. Hyperion is not tidally locked. It tumbles chaotically. Its rotation period changes unpredictably. Sometimes it's rotating fast, sometimes slow. The axis of rotation wobbles. There's no pattern, no predictability. This is called chaotic rotation, and Hyperion is one of the few objects in the solar system that exhibits it. Why? The main reason is Hyperion's shape. It's not spherical. It's irregular, roughly shaped like a potato, or maybe a slightly squashed ellipsoid. It's about 360 kilometers long and 280 kilometers across at its widest. This irregular shape means the gravitational torques from Saturn are complex. As Hyperion orbits, different parts of it face Saturn at different times. Saturn's gravity pulls on these different parts with varying strength. For a spherical moon, these torques average out and lead to tidal locking. But for an irregularly shaped moon like Hyperion, the torques can cause the rotation to become chaotic. There's also the fact that Hyperion's orbit is slightly eccentric, and it's in a resonance with Saturn's much larger moon, Titan. This means Hyperion's orbital speed varies, which affects the tidal torques. Add it all up, and you get chaos. Computer simulations show that Hyperion's rotation is genuinely chaotic in the mathematical sense. That means it's sensitive to initial conditions. A tiny change in its rotation state would lead to completely different tumbling behavior over time. You can't predict how Hyperion will be oriented even a few months in advance, because the system is chaotic. This is unusual. Most celestial mechanics are predictable. We can calculate planetary positions decades or even centuries in advance with high accuracy. But Hyperion's rotation, unpredictable. It's deterministic chaos. The physics is deterministic. There's no randomness in the equations, but the outcome is unpredictable because of sensitivity to initial conditions. Now imagine you're on the surface of Hyperion. What would the sky look like? Saturn would be visible, enormous and beautiful, but its position in the sky would change unpredictably. Sometimes it would be overhead, sometimes on the horizon, sometimes rising, sometimes setting. There would be no pattern to Saturn's motion across Hyperion's sky, and the length of a day on Hyperion would change constantly. Sometimes a day might be a few Earth days long, sometimes longer, sometimes shorter. There's no stable day-night cycle. The sun would rise and set at unpredictable intervals from unpredictable directions. It would be disorienting. Here's another strange thing about Hyperion. Despite its chaotic rotation, it's been this way for millions or billions of years. Normally, tidal forces from a planet will eventually stabilize a moon's rotation. Over time, energy is dissipated, and the moon settles into a stable state, usually tidal locking. But Hyperion hasn't stabilized. It's thought that this is because Hyperion is so porous and has such low density. The energy dissipation that would normally slow the rotation and stabilize it happens very slowly in Hyperion's spongy interior, so it's been tumbling chaotically for a very long time, and it might continue doing so for a very long time. Hyperion is also notable for another reason. Its surface is unusually dark in some regions. The deep craters have material that's much darker than the surrounding surface. This dark material is probably organic compounds, tholins, that have accumulated in the craters. Tholins form when ultraviolet light and cosmic rays interact with simple organic molecules like methane. Over time, these reactions produce complex, dark, reddish-brown compounds. We see tholins on other objects in the outer solar system, like Titan and Pluto, but on Hyperion, the tholins have collected in the crater bottoms, creating striking dark patches. It gives Hyperion an even more otherworldly appearance. Hyperion is a reminder that moons can be just as strange as planets. We tend to think of moons as simple, boring, just rocks orbiting planets. But Hyperion shows that moons can have complex, chaotic dynamics. They can have bizarre surface features. They can be porous sponges tumbling unpredictably through space. And we only discovered all of this in the last few decades, when Cassini visited Saturn and studied its moons up close. Before Cassini, Hyperion was just a faint dot in telescopes. Now we know it's one of the strangest moons in the solar system. A chaotic tumbler with a sponge-like surface and dark organic material pooling in its craters. It's weird, and it's wonderful. 16. The TRAP. PIST. 1. System in 2017. Astronomers made an announcement that sent ripples through the scientific community and captured public imagination. They'd found 7 Earth-sized planets orbiting a single star, and 3 of them were in the habitable zone. The star is called TRAP-PIST-1. It's a small, cool, red dwarf star about 40 light-years away in the constellation Aquarius. It's tiny compared to the Sun, only about 9% of the Sun's mass, roughly the size of Jupiter. If you were standing on Earth and looked up at TRAP-PIST-1, it would be so faint you'd need a telescope to see it. But despite being small and dim, TRAP-PIST-1 has 7 planets. They're labeled TRAP-PIST 1b through T, RAP-PIST 1H, moving outward from the star. All 7 are roughly Earth-sized. Some are slightly smaller, some slightly larger, but they're all in the same ballpark. This is remarkable because finding Earth-sized planets is hard. Most exoplanets we've discovered are much larger. Gas giants like Jupiter or Neptune-sized ice giants. Small rocky planets like Earth are harder to detect because they cause smaller dips in their star's light when they pass in front of it. But TRAP-PIST-1 is so small and dim that even Earth-sized planets cause noticeable dips. That's how we found them, by watching the star and measuring how its brightness changed as planets passed in front of it. This method is called the transit method, and it's how we've discovered most exoplanets. The TRAP-PIST, planets transit regularly. And because there are 7 of them, the star's light is almost constantly dipping as one planet or another passes in front. By studying these transits carefully, astronomers learned a lot about the planets. They measured their sizes. They estimated their masses by looking at how they gravitationally tug on each other. They figured out their orbital periods, how long each planet takes to complete one orbit around the star. And here's where it gets interesting. The planets are close to the star, very close. The innermost planet, TRAP-PIST 1b, orbits in just 1.5 Earth days. The outermost planet, TRAP-PIST 1H, orbits in about 20 Earth days. All 7 planets orbit closer to their star than Mercury orbits the Sun. If you mapped the TRAP-PIST-1 system onto our solar system, all 7 planets would fit inside Mercury's orbit. They're packed together. But here's the thing. TRAP-PIST-1 is so cool and dim that even though the planets are close, they're not all scorched. The inner planets are probably too hot for liquid water. Their surfaces would be baked. But the middle planets, TRAP-PIST, 1E, F, and G, are in the habitable zone. The habitable zone is the region around a star where temperatures are right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. Of course, being in the habitable zone doesn't guarantee a planet is habitable. You also need the right atmosphere, the right composition, the right conditions. But it's a start. 3 potentially habitable Earth-sized planets in a single system. That's unprecedented. Now let me tell you what it would be like to stand on one of these planets. Let's say you're on TRAP-PIST 1E, which is right in the middle of the habitable zone. The first thing you'd notice is the sky. TRAP-PIST 1 is a red dwarf. It's much cooler than the Sun, so it emits mostly red and infrared light. The sky wouldn't be blue like Earth's. It would be a strange, salmon-red color. The star would appear enormous in the sky. About 10 times larger than the Sun appears from Earth. Even though it's much dimmer than the Sun, it would dominate the sky because you're so close to it, and it would barely move. The TRAP-PIST One planets are probably tidally locked, just like Earth's moon is tidally locked to Earth. This means one side of the planet always faces the star. The other side always faces away. On the day side, the red dwarf would hang in the sky, never setting. On the night side, it would always be dark. There would be no day-night cycle like on Earth. Just permanent day on one hemisphere and permanent night on the other. The boundary between day and night, called the terminator, would be a twilight zone, a ring around the planet where the star is always on the horizon. This is probably the most habitable region, not too hot, not too cold. But here's something even stranger. Because the planets are so close together, you'd be able to see the other planets in the sky. From TRAP, PIST, 1E, the neighboring planets, would appear larger than the moon appears from Earth. You'd see them as actual disks, not just points of light, and you'd watch them go through phases, like Venus does from Earth. Sometimes they'd be crescents, sometimes full, sometimes in between. The sky would be a constantly changing display of planetary motions. Imagine looking up and seeing 3 or 4 other Earth-sized worlds hanging in the sky, some closer, some farther, all slowly moving in their orbits. It would be spectacular. Now, are these planets actually habitable? We don't know yet. The James Webb Space Telescope has observed the TRAP, PIST, 1 planets trying to detect their atmospheres. Early results are mixed. Some planets might have atmospheres, others might not. TRAP, PIST. 1B and C, the innermost planets, probably don't have thick atmospheres. They're too hot, and any atmosphere would have been stripped away by the star's radiation. But the outer planets might have atmospheres. The challenge is detecting them. Atmospheres are thin, and the signal is faint. Webb is looking for signs of water vapor, carbon dioxide, methane, oxygen, molecules that would tell us what these atmospheres are made of. If we find oxygen in significant amounts, that would be really interesting. On Earth, oxygen is produced by life, plants, and photosynthetic bacteria. Finding oxygen on a TRAP, PIST, 1 planet, would be a strong hint of life, but it's not a guarantee. Oxygen can also be produced by non-biological processes. Still, it would be exciting. We're in the early stages of studying these planets. It'll take years of observations to build up a clear picture, but the potential is enormous. 7 Earth-sized planets, 3 in the habitable zone, close enough that we can study them in detail with current technology. This is one of the best opportunities we have to search for life beyond Earth. Here's something else to consider. The TRAP, PIST, 1 system is tightly packed. The planet's orbits are in resonances with each other. For every orbit that one planet makes, another planet makes a certain number of orbits. The ratios are simple integers. This resonance keeps the orbits stable. The planets' gravitational interactions reinforce each other rather than destabilizing the system. It's similar to the resonance between Jupiter's moons Io, Europa, and Ganymede. This suggests that TRAP, PIST, 1 planets formed in place or migrated inward together early in the system's history. They're a family. They've been together for billions of years. TRAP, PIST, 1 is old, probably around 8 billion years old, older than the Sun. That means the planets have been around for a long time. If life exists on any of them, it's had billions of years to develop. That's both exciting and sobering. Exciting because life would have had plenty of time to evolve into complex forms. Sobering because if life had billions of years and we don't see obvious signs of it, maybe it's not there. Or maybe it is there, but not producing detectable biosignatures. Or maybe we're just not looking in the right way yet. the TRAP-PIST. One system is a reminder that the universe is full of worlds. Not just gas giants orbiting distant stars, but Earth-sized planets in habitable zones. Worlds where, in principle, life could exist. We don't know if TRAPPIST-1 hosts life. We might never know for sure without sending a probe, which won't happen in our lifetimes, given the distance. But we can study the planets from here. We can search for signs, and every observation brings us closer to answering one of humanity's oldest questions. Are we alone? The TRAPPIST. One system might hold the answer. 7 worlds, 40 light-years away, waiting to be understood. 17. Quasar J03131806. In 2021, astronomers announced the discovery of the most distant quasar ever found. They called it J03131806, and it's so far away that we're seeing it as it was just 670 million years after the Big Bang. The universe is 13.8 billion years old. This quasar existed when the universe was only 5% of its current age. That's remarkable on its own. But here's what makes it truly bizarre. The quasar contains a supermassive black hole with a mass of about 1.6 billion suns. Let me repeat that. 1.6 billion solar masses. When the universe was only 670 million years old. This shouldn't be possible. Let me explain why. Black holes grow by consuming matter. Gas, dust, stars, anything that falls in. But there's a limit to how fast they can grow. It's called the Eddington limit. When a black hole feeds, the infalling matter heats up and emits radiation. This radiation exerts pressure, pushing matter away. If a black hole tries to feed too fast, the radiation pressure becomes so strong it stops matter from falling in. This limits the growth rate. Based on the Eddington limit, you can calculate how long it would take a black hole to grow to a certain size. Start with a seed black hole, maybe a stellar mass black hole from a massive star, say 100 solar masses. Let it grow at the Eddington limit for 670 million years. It would reach maybe a few million solar masses, maybe tens of millions if conditions were perfect, not 1.6 billion. The black hole in J0313, 1806, is about 100 times more massive than it should be. So how did it get so big, so fast? There are several ideas, none of them entirely satisfying. Idea 1. Maybe the seed black hole was much larger than we thought. Instead of starting from a stellar mass black hole, maybe it started from something bigger. Some theories propose that in the early universe, massive clouds of gas could collapse directly into large black holes without forming stars first. These direct collapse black holes could have masses of thousands or even hundreds of thousands of suns right from the start. If J0313-1806's black hole started that large, it would have had a head start. Growing from 100,000 solar masses to 1.6 billion is still a stretch, but it's more plausible than growing from 100. The problem is, we've never observed a direct collapse black hole forming. It's theoretical. Idea 2. Maybe the black hole grew faster than the Eddington limit allows. This is called super-Eddington accretion. Under certain conditions, a black hole might be able to accrete matter faster than the Eddington limit predicts. Maybe if the inflow is very dense and cold, radiation can't escape efficiently, so it doesn't push matter away as effectively. Or maybe the accretion is clumpy, with dense clouds falling in that aren't affected by radiation pressure the same way diffuse gas would be. Computer simulations show that super-Eddington accretion is possible, but it requires specific conditions. And even with super-Eddington accretion, it's hard to grow a black hole to 1.6 billion solar masses in just 670 million years. Idea 3. Maybe the black hole grew through mergers. If multiple smaller black holes merged together, they could form a larger black hole faster than accretion alone would allow. In the early universe, galaxies were smaller and closer together. Mergers were more common. Maybe J0313-1806's black hole is the result of many mergers. The challenge is that mergers take time. Black holes need to find each other, spiral together, and merge. And after each merger, the system needs to settle down before the next accretion phase can begin. It's unclear if mergers alone can explain such rapid growth. Idea 4. Maybe our understanding of the early universe is wrong. Maybe conditions were different than we think. Maybe there was more gas available, or it was distributed differently, allowing black holes to grow faster. Maybe the first stars were much more massive than we thought, creating larger seed black holes. This is the "we don't know what we don't know" option. It's possible, but it's not very satisfying because it doesn't give us a specific mechanism. Here's what really bothers me about J0313-1806. It's not alone. Since its discovery, astronomers have found other extremely distant quasars with supermassive black holes. Not all are as massive as J0313-1806, but many are still too massive for their age. This suggests that whatever process created these black holes wasn't a fluke. It happened multiple times in the early universe. That means there's something systematic we don't understand about black hole formation and growth in the early universe. Maybe the first stars were different. Maybe direct collapse black holes were common. Maybe accretion was faster. We don't know. What we do know is that the early universe was more active and complex than our models predicted. Galaxies formed earlier. Stars formed earlier. Black holes grew faster. The universe hit the ground running, so to speak. There wasn't a long, slow build-up. Things happened quickly. J0313-1806 is also interesting because it tells us about the conditions in the early universe. The quasar is bright because matter is falling into the black hole, heating up and emitting enormous amounts of energy. This energy affects the surrounding galaxy. It heats gas, potentially preventing it from forming stars. It creates powerful winds that blow gas out of the galaxy. This is called feedback, and it plays a crucial role in how galaxies evolve. The fact that J0313-1806 is so bright means it's having a major impact on its host galaxy. Even at this early stage, just 670 million years after the Big Bang, black holes were already influencing galaxy evolution. This feedback process is thought to be why there's a relationship between black hole mass and galaxy mass in the present-day universe. Bigger galaxies have bigger black holes, not randomly, but in a predictable ratio. J0313-1806 shows that this relationship was already being established very early. Studying distant quasars like J0313-1806 is challenging. They're incredibly far away. The light has been traveling for over 13 billion years. By the time it reaches us, it's redshifted into the infrared. The James Webb Space Telescope is perfect for studying these objects. Webb can see in infrared. It can observe distant quasars and galaxies in unprecedented detail. Since its launch, Webb has found even more distant quasars and galaxies. Each new discovery pushes back the timeline of when things formed, and each one raises more questions about how the early universe worked. J0313-1806 is a signpost. It's telling us that our models of the early universe need refinement. Black holes grew faster than we thought. Galaxies formed earlier than we thought. The universe was more precocious than we expected, and somewhere, 13 billion years ago, a black hole 1.6 billion times the mass of the Sun was already shining brightly, doing something that shouldn't have been possible yet, challenging our understanding, making us rethink what we know. 18. The Bullet Cluster in 2006. Astronomers released an image that became one of the most important pieces of evidence for dark matter. It's called the Bullet Cluster, and it's actually two galaxy clusters that collided with each other. The collision happened about 150 million years ago. We're seeing the aftermath. At first glance, it looks like any other galaxy cluster, hundreds of galaxies scattered across space. But when astronomers overlaid different observations on the same image, something strange appeared. They used three types of observations. First, visible light images showing where the galaxies are. Second, X-ray images showing where the hot gas is. Galaxy clusters contain enormous amounts of hot gas between the galaxies. This gas is so hot, it emits X-rays. Third, gravitational lensing maps showing where the mass is. Gravitational lensing is a technique where you look at how light from distant background galaxies gets bent as it passes through a massive object. The amount of bending tells you how much mass is there. When astronomers combined these three observations, they saw something remarkable. The galaxies were in one place. The hot gas was in another place, and the mass, as determined by gravitational lensing, was in yet another place. They weren't aligned. Let me explain what happened. Two galaxy clusters collided at high speed, about 4,700 kilometers per second. When they collided, the galaxies mostly passed through each other without colliding. Space is mostly empty. Even in a galaxy cluster, the galaxies are far apart, so they sailed through without much interaction. But the hot gas didn't pass through. The two clusters each contained huge clouds of hot gas. When these gas clouds collided, they slammed into each other. Gas doesn't pass through gas. They interact. The collision heated the gas even further and slowed it down, so the hot gas got left behind, in between the two clusters that had passed through each other. That's why the X-ray emission, which traces the hot gas, is in a different location than the galaxies. The gas got separated from the galaxies during the collision. But here's the weird part. The gravitational lensing maps, which show where the mass is, don't match the gas distribution either. Most of the mass is with the galaxies, not with the gas. Wait, that's strange. In galaxy clusters, the hot gas makes up more mass than the galaxies do. Typically, the gas accounts for about 90% of the ordinary matter in a cluster. The galaxies account for only 20%. So, if gravitational lensing is showing us where the mass is, it should be concentrated where the gas is. But it's not. The mass is concentrated where the galaxies are. This means there's a lot of mass with the galaxies that we can't see. Mass that doesn't emit light. Mass that doesn't interact with the gas. Mass that passed right through the collision without slowing down, just like the galaxies did. This is dark matter. The Bullet Cluster is one of the clearest, most direct pieces of evidence that dark matter exists and that it's separate from ordinary matter. Here's why this observation is so important. For decades, scientists have inferred the existence of dark matter from various observations. Galaxies rotate in ways that suggest they contain more mass than we can see. Galaxy clusters are held together by gravity that requires more mass than the visible matter provides. The cosmic microwave background has patterns that require dark matter to exist, but all of these are indirect evidence. You're inferring dark matter's existence from its gravitational effects. Some scientists proposed alternative theories. Maybe we don't need dark matter. Maybe gravity works differently on large scales. These theories are called modified Newtonian dynamics, or MOND. MOND theories can explain some observations without invoking dark matter, but the Bullet Cluster is a problem for MOND. In the Bullet Cluster, the mass and the ordinary matter are clearly separated. The gravitational lensing, which directly measures where the mass is, doesn't match the distribution of stars and gas. The only way to explain this is if there's a large amount of invisible matter that passed through the collision without interacting. That's exactly what dark matter should do. Dark matter doesn't interact with ordinary matter, except through gravity. It doesn't collide like gas does. It doesn't emit light like stars do. It's just mass. Invisible, non-interacting mass. When the two clusters collided, the dark matter in each cluster passed right through without slowing down, just like the galaxies did. So now, after the collision, the dark matter is still with the galaxies. The gas got left behind. But the dark matter kept going. That's why the gravitational lensing maps show the mass concentrated with the galaxies, not with the gas. This observation is very hard to explain without dark matter. You'd have to come up with a modified gravity theory that can somehow separate the gravitational effects from the matter distribution. That's much more complicated than just accepting that dark matter exists. The bullet cluster has become a key piece of evidence in the dark matter debate. It's not the only evidence, but it's one of the clearest. Since the bullet cluster, astronomers have found other colliding clusters with similar properties. Each one reinforces the conclusion that dark matter is real and separate from ordinary matter. Now, what is dark matter? That's the big question. We know it exists. We can measure its gravitational effects. But we don't know what it's made of. The leading candidates are weakly interacting massive particles, or WIMPs. These are hypothetical particles that have mass, but don't interact with light or ordinary matter, except through gravity, and possibly the weak nuclear force. Experiments have been searching for WIMPs for decades. Deep underground detectors waiting for a dark matter particle to collide with ordinary matter. So far, no definitive detection. Other candidates include axions, sterile neutrinos, and more exotic possibilities. But we don't know. The bullet cluster tells us dark matter exists. It doesn't tell us what it is. That's the next step. And it's one of the biggest unsolved problems in physics. What I find fascinating about the bullet cluster is how clearly it shows the separation. You can literally see, in one image, three different components: the galaxy's invisible light, the gas in X-rays, the mass in gravitational lensing, all in different places. It's a cosmic train wreck that laid bare the structure of galaxy clusters, and in doing so, it provided some of the strongest evidence for one of the most mysterious components of the universe: dark matter. Invisible, non-interacting, making up 85% of the matter in the universe. And we can see its effects clearly in the bullet cluster. Two galaxy clusters colliding at thousands of kilometers per second. The galaxies passing through. The gas colliding and slowing. And the dark matter, invisible, passing through without a trace, except for the gravitational signature it leaves behind. 19. Epsilon Aurigui. There's a star in the constellation Auriga called Epsilon Aurigui. It's visible to the naked eye. You can see it without a telescope if you know where to look. But every 27 years, something strange happens. The star starts to dim. Over the course of several months, it fades to about half its normal brightness. It stays dim for almost 2 years. Then it slowly brightens again, returning to normal over several more months. The entire eclipse lasts about 2 years out of every 27. This has been happening for as long as we've been watching. The first recorded eclipse was in 1821. So what's causing it? Something is passing in front of the star, blocking its light. An eclipsing companion. Another object in orbit around Epsilon Aurigui. But here's the mystery. We can't see what the companion is. For nearly 200 years, astronomers have been trying to figure out what's eclipsing Epsilon Aurigui. Let me tell you what we know. Epsilon Aurigui itself is a supergiant star, huge and luminous. Its radius is about 150 times the Sun's radius. If you put it where the Sun is, its surface would extend well beyond Earth's orbit. It's also bright, about 130,000 times more luminous than the Sun. This star is so large and bright that whatever is eclipsing it has to be enormous. To block half the star's light for 2 years, the eclipsing object has to be huge. But we don't see it. When the eclipse isn't happening, we should see light from the companion. But we don't. Or at least, we don't see light in the wavelengths we'd expect. This tells us the companion is dark or heavily obscured. For decades, astronomers proposed various theories. Maybe the companion is a large dark disk of material, a protoplanetary disk around a young star. Maybe it's a binary system of smaller stars surrounded by a dusty disk. Maybe it's something even more exotic. The problem was, without better observations, we couldn't test these theories. Then came the 2009-2011 eclipse. Astronomers prepared for this eclipse like never before. They pointed every available telescope at Epsilon Aurigae, optical telescopes, infrared telescopes, interferometers. The goal was to gather enough data to finally solve the mystery, and they made progress. Using a technique called interferometry, where you combine light from multiple telescopes to effectively create a much larger telescope, astronomers were able to resolve some details of the system. What they found was surprising. The companion appears to be a disk of material, a dark, opaque disk oriented edge-on to us. The disk is about 4 AU across. That's 4 times the distance from Earth to the Sun. Inside this disk, there might be 1 or 2 smaller stars, but they're completely hidden by the disk material. The disk itself is made of dust and gas. It's cold and dark, which is why we don't see it emitting much light. When the disk passes in front of Epsilon Aurigae, it blocks the star's light, causing the eclipse. But this raises more questions. Why is there a disk? Where did it come from? One idea is that the disk is a circumbinary disk. The companion is actually a binary star system, 2 stars orbiting each other. Around this binary pair is a disk of material, perhaps left over from the star's formation. Or maybe the disk was created by mass transfer, material from one star flowing to the other and forming a disk in the process. Another idea is that the disk is the remains of a planet or smaller star that was destroyed. Maybe something got too close to the companion, was torn apart by tidal forces, and formed a disk. These explanations are plausible, but we're not certain. The 2009-2011 eclipse gave us more data than ever before, but the system is still not fully understood. What makes Epsilon Aurigae particularly frustrating is that we have to wait 27 years between eclipses. We got good data in 2009-2011. The next eclipse will be in 2036-2038. That's when we'll get our next chance to study the system in detail. By then, we'll have better telescopes, better instruments, more sophisticated analysis techniques. Maybe we'll finally solve the mystery completely. Or maybe we'll find new mysteries. That's how astronomy often works. Here's what I find fascinating about Epsilon Aurigae. It's been a mystery for 200 years. Generations of astronomers have observed it. They've proposed theories, gathered data, argued about interpretations, and we still don't have all the answers. That's humbling. We can send spacecraft to the edge of the solar system. We can detect gravitational waves from colliding black holes billions of light years away. But we can't fully explain what's happening in a star system that's visible to the naked eye, just 2,000 light-years away. Epsilon Aurigae reminds us that even relatively nearby objects can be mysterious. It also reminds us that astronomy requires patience. We have to wait for eclipses. We have to wait for stars to change. We have to wait for light to travel across space. We can't rush the universe. We have to work on its schedule. So we observe. We gather data. We build models. We wait for the next eclipse. And slowly, over decades and centuries, we piece together the story. Epsilon Aurigae is still being written. Every 27 years, the dark companion passes in front of the star. For 2 years, it blocks the light, and we watch, gathering clues, trying to understand what's happening in this strange system. A supergiant star and its mysterious dark companion, orbiting each other every 27 years, hiding their secrets behind a veil of dust. 20. The Pillars of Creation's Destruction. In 1995, the Hubble Space Telescope captured one of the most iconic images in astronomy. 3 towering columns of gas and dust in the Eagle Nebula. They called it the Pillars of Creation. The pillars are regions of star formation, dense clouds of gas and dust where new stars are being born. They're beautiful, majestic. They look like cosmic sculptures reaching up into space. The image became famous. It appeared in textbooks, documentaries, posters. It's one of the most recognizable astronomical images ever taken. But here's something most people don't know. The pillars of creation might already be destroyed. Let me explain. The Eagle Nebula is about 7,000 light-years away from Earth. That means the light we see from it took 7,000 years to reach us. We're not seeing the nebula as it is now. We're seeing it as it was 7,000 years ago. In 2007, astronomers using the Spitzer Space Telescope found evidence of a supernova shockwave in the region of the Eagle Nebula. The shockwave appears to be moving toward the pillars of creation. Based on the shockwave's speed and position, astronomers calculated when it would have reached the pillars. The answer, about 6,000 years ago. If that's correct, the pillars were hit by a supernova shockwave about 6,000 years ago, and that shockwave would have been powerful enough to destroy them. The dense gas and dust of the pillars would have been heated, ionized, and blown apart by the intense energy of the shockwave. Within a few thousand years, the pillars would have been eroded away. Nothing would be left but diffuse gas. But here's the thing. We can't see this yet. The pillars are 7,000 light-years away. Light showing the destruction would have left the pillars about 6,000 years ago. It's been traveling toward us for 6,000 years. It still has about 1,000 years to go before it reaches Earth. So, from our perspective, the pillars still exist. We can still see them in telescopes. But in reality, in the present moment, they're probably gone. They've been destroyed for millennia. We just haven't gotten the news yet. This is one of the strangest things about astronomy. We're always looking into the past. Light takes time to travel, so everything we see is delayed. The sun we see is 8 minutes old. The light left the sun 8 minutes ago. If the sun exploded, we wouldn't know for 8 minutes. For distant objects, the delays are much longer. The Andromeda Galaxy is 2.5 million light-years away. The light we see from it is 2.5 million years old. When we look at distant galaxies billions of light-years away, we're seeing them as they were billions of years ago. Many of those galaxies have changed or even ceased to exist by now. We just don't know it yet. The pillars of creation are a local example of this phenomenon. They're close enough that we can see them in detail. We've studied them extensively, but they might already be gone. Now, to be clear, this isn't certain. The evidence for the supernova shockwave is strong, but there's some uncertainty in the timing and trajectory. Maybe the shockwave missed the pillars, maybe it only grazed them, causing some damage but not complete destruction. Or maybe the calculations are slightly off, and the shockwave hasn't reached them yet. We won't know for sure until the light showing the aftermath reaches us, and that won't happen for about another 1,000 years. So future generations, around the year 3000, might watch the pillars of creation get destroyed. They'll see the shockwave hit. They'll see the pillars erode and disappear. But for us, in 22,005, the pillars still stand. We can still observe them. We can still study star formation happening within them, even though in reality they might be long gone. This time delay creates a weird situation. Astronomers in the year 3000 will have knowledge we don't have. They'll know whether the pillars were destroyed, but they'll also know that in our era, in 2025, the pillars still appeared intact. They'll understand that we were seeing an outdated image. Meanwhile, we can speculate based on the supernova evidence, but we can't know for certain. It's a form of cosmic uncertainty imposed by the speed of light. There's something poetic about this. The pillars of creation, one of the most beautiful and celebrated structures in space, might only exist in the past. They're a monument to something that's already gone. And yet, they're still creating stars. Or at least, they were 7,000 years ago. Some of the stars being born in the pillars, in the images we see, might still exist today. They would have formed, ignited, and begun their lives in the pillars before the shockwave hit. If the shockwave destroyed the pillars 6,000 years ago, those stars are now 6,000 plus years old, young stars drifting in the remnants of their birthplace. Eventually, the gas and dust blown apart by the shockwave might coalesce again. It might form new clouds, new pillars, new regions of star formation. The cycle continues. Destruction leads to creation. Creation leads to destruction. The universe recycles itself. The pillars of creation are a snapshot of one moment in this cycle, a beautiful moment, captured by Hubble, frozen in time. But the universe doesn't freeze. It moves forward, constantly changing. And somewhere, 7,000 light-years away, the pillars are either still standing or they've been reduced to scattered gas, glowing faintly in the aftermath of a shockwave. We won't know which until light from the present moment reaches us, in about 1,000 years. Until then, we can look at the images and wonder, are we looking at something that still exists, or a ghost, a structure preserved in light, traveling across space, carrying information from 7,000 years ago? The pillars of creation might be the pillars of destruction by now, but we can't see it yet. The universe keeps its secrets hidden in the time it takes for light to travel, and we're left looking at the past, calling it the present, and wondering what the real present looks like.